Hello there, and welcome to Just About Earth, where curiosity slows its pace and science takes the long, gentle road toward rest. Tonight's quiet journey circles around a question that feels both enormous and strangely intimate, like asking whether the ground beneath your feet once shared the same breath as every other corner of the planet. Did Earth, long before our familiar patterns of deserts and rainforests, winters and summers, once move under a single sweeping climate that reached everywhere at once? It's a thought that stretches the imagination in the softest way, like trying to picture the entire world wrapped in the same kind of weather, the same air, the same sky, from pole to pole. Before we begin drifting into that story, I'd love to know something small and human. Where are you listening from tonight? Are you in a room lit by a lamp, a phone screen, or maybe just the pale glow of the moon through a window? And what time is it for you right now, in your own quiet corner of the planet that's about to take centre stage in this tale? If you find this space soothing, or if it helps the day loosen its grip just a little, you're always welcome to like the video or subscribe. It helps this calm little pocket of curiosity find its way to others who might need a slower moment too. Now, let's begin with an image that doesn't belong to any postcard or weather report you've ever seen. Imagine standing on a piece of land that doesn't yet know what a season is. There's no concept of summer heat or winter cold, no dry months followed by rainy ones, no predictable rhythm of storms moving across maps. Instead, the air around you feels like part of something larger, something that stretches far beyond the horizon in every direction. A kind of shared atmosphere that doesn't care where one place ends and another begins. The wind that brushes past your face is the same wind, in a sense, that will circle the globe. The clouds overhead are not part of a regional pattern, but part of a planetary one. This is the idea at the heart of our question. Not just that Earth's climate was different in the deep past, which we already know it was, but that it may have been unified in a way that feels almost foreign to us now. Today, the planet is a patchwork. Tropical rainforests breathe moisture into the air near the equator. Vast deserts hold on to heat under wide open skies. Polar regions lock water away in ice and snow. Mountain ranges catch clouds and cast rain shadows. Every place has its own weather personality, shaped by latitude, altitude, oceans, and the slow movement of continents. It's easy to forget that this diversity is the result of a long, complicated history rather than a permanent feature of the world. To start unravelling that history, it helps to step back so far in time that even the familiar outline of the continents disappears. If you could look down at Earth billions of years ago, you wouldn't recognise it as home. The land was sparse, broken into smaller pieces, or in some eras clustered into enormous supercontinents. The oceans covered more of the surface, darker and often warmer than the ones we know today. The sky itself would have looked different, tinted by gases that no longer dominate our atmosphere. Oxygen, the thing we quietly depend on with every breath, was once a trace ingredient rather than a defining feature. In that kind of world, climate didn't behave the way it does now. Without tall mountain chains to redirect winds or large ice caps to reflect sunlight back into space, the systems that move heat and moisture around the planet may have been simpler, broader, and more connected. Warm water from the equator could flow more freely toward the poles. Air currents could circle the globe with fewer obstacles. The idea of a single, overarching climate starts to feel less like a poetic exaggeration, and more like a plausible chapter in Earth's long biography. One of the first things to consider is the role of the Sun. Billions of years ago, our star was not quite the same as it is today. It was slightly dimmer, putting out less energy. This creates a puzzle that scientists still enjoy turning over in their minds. If the Sun was weaker, why wasn't the early Earth a frozen world? The answer seems to lie in the atmosphere. Gases like carbon dioxide and methane were more abundant, trapping heat and keeping the surface warm enough for liquid water to exist. In a way, the planet wrapped itself in a thicker thermal blanket. That blanket didn't just keep things warm in one place, it affected the whole globe. With fewer contrasts between hot and cold regions, the difference between equator and pole may have been smaller. Temperature gradients, the driving force behind many of today's powerful weather systems, might have been gentler. Instead of sharp boundaries where warm air crashes into cold air to form storms, there could have been broad, slow-moving patterns that felt more like a steady circulation than a series of dramatic events. Oceans, too, played a part in this connected world. Water is an excellent transporter of heat. Even now, currents like the Gulf Stream carry warmth from the tropics toward the North Atlantic, shaping the climate of entire continents. In a planet with different land arrangements and fewer barriers, these currents may have been even more influential. Imagine a vast, uninterrupted ocean wrapping around most of the globe, allowing heat to move in long, looping paths. The result would be a kind of planetary thermostat, smoothing out extremes and helping maintain a more uniform climate. There's a quiet elegance to this idea. Earth, in its youth, as a place where the line between one region and another was blurred not just on maps, but in the air and water themselves. A world where the concept of local weather hadn't yet taken shape, because the whole planet was participating in the same slow, shared process of warming and cooling, breathing in sunlight and breathing out heat. Of course, this doesn't mean everything was calm or comfortable. A unified climate doesn't have to be a gentle one. In fact, some of the most dramatic events in Earth's history suggest that when the planet did act as a single system, it could swing to extremes. There were times when ice may have reached all the way to the equator, turning the world into what scientists now call a snowball Earth. In those periods, glaciers likely covered vast stretches of land, and the oceans may have been capped with ice from pole to pole, broken only by occasional openings near volcanic activity or along cracks in the frozen surface. If that picture is accurate, then the planet truly did share a single climate, but one defined by cold and reflection rather than warmth and circulation. Sunlight bounced off the bright, icy surface back into space, reinforcing the chill. It would have been a feedback loop on a global scale, one that didn't care where you were standing because everywhere was part of the same frozen system. What's remarkable is that Earth didn't stay that way. Over time, volcanic eruptions continued to release carbon dioxide into the atmosphere. With ice covering much of the surface, the usual processes that remove carbon dioxide, like the weathering of rocks, slowed down. The gas built up, thickening the atmospheric blanket once again. Eventually the balance tipped. Temperatures rose, ice melted, and the planet thawed, not just in one region but across the world. Imagine the sound of that if you could hear it. Not the crack of a single glacier breaking, but the slow, planet-wide release of water. As ice gave way to liquid, rivers began to flow and oceans reconnected with the sky. These kinds of transitions hint at a deeper truth. Earth's climate has always been a global system, even when we experience it locally. The difference in the past may have been a matter of degree. The connections between regions were stronger, the contrast weaker. The planet behaved more like a single unified machine, responding as a whole to changes in sunlight, atmospheric composition, and the restless movement of its interior. Another piece of this story lies in the slow dance of the continents. The ground beneath your feet is not fixed in place over geological time. Plates of crust drift across the surface, colliding, pulling apart, and reshaping the face of the planet. When land masses cluster together into a supercontinent, as they have several times in Earth's history, the climate tends to become more extreme. The interior of such a vast landmass can be far from the moderating influence of the oceans, leading to hotter summers and colder winters. But the oceans themselves, now arranged in different patterns, can circulate heat in new ways, sometimes creating a more unified system across the water-covered majority of the planet. It's a reminder that the idea of a single climate doesn't have to mean uniform conditions everywhere. Instead, it can mean a world where the major controls on temperature, moisture, and atmospheric movement operate at a planetary scale, with fewer interruptions from the kind of geographic features we take for granted today. Life, quietly, was part of this story too. Even the smallest organisms can influence the atmosphere. Early microbes, through processes like photosynthesis, began to change the balance of gases in the air. Over immense spans of time, these changes affected how much heat the planet retained, which in turn influenced ice, oceans, and winds. It's a subtle, almost circular relationship. Climate shapes life, and life, in its own slow way, reshapes climate. On a young Earth with fewer complex ecosystems, those interactions may have been simpler, but no less profound in their cumulative effect. Thinking about all this can feel a bit like standing at the edge of a very deep pool. You can see the surface clearly enough, but the deeper you look, the more the details blur and fade into something vast and quiet. The idea that our planet once moved under a more unified climate invites that kind of reflection. It asks you to imagine Earth not as a collection of countries, biomes and weather forecasts, but as a single breathing system, responding to forces that come from both within and beyond. There's something gently humbling about that perspective. The rain that falls on one side of the world, the sunlight that warms another, the volcanic gases that drift into the upper atmosphere, all of it becomes part of a shared story. Even now, in our modern, highly detailed understanding of climate, scientists talk about the Earth system as a whole. The deep past simply reminds us that this idea isn't new. It's woven into the very nature of a planet that spins under one sun and holds onto one continuous envelope of air and water. As you sit with this thought, maybe let your attention wander back to where you are right now. The room you're in has its own temperature, its own little climate. Perhaps there's a hum from a heater or a soft breeze from a fan. Outside, the weather is doing whatever it's doing, shaped by currents and pressures that stretch far beyond your street or city. In a small way, you're already part of a global system, even if it doesn't always feel like it. What we've done here is open a door, just slightly, onto a much longer journey. We've touched the idea of a planet that once may have acted more like a single coordinated whole, guided by broad, powerful forces rather than the intricate patchwork we see today. There are deeper layers to explore, moments in Earth's past where this unity was tested, broken, and reshaped. The clues to those moments are written in rocks, ice, and the chemistry of ancient seas, waiting patiently for us to notice them. So, as we ease forward, keep that image in mind. A world where the air itself felt like a shared breath, where oceans and skies worked together in long, looping patterns that wrapped around the globe. From there, it becomes a little easier to follow the traces left behind. The quiet evidence that suggests Earth's climate story is not just a series of local tales, but a single, unfolding narrative that stretches across billions of years. Long before maps divided the world into continents, countries and carefully labelled climate zones, there was a version of Earth that didn't recognise any of those boundaries. If you could stand back far enough, far beyond clouds and orbiting satellites, and look down at the planet as a whole, you wouldn't see a mosaic of different weather patterns stitched together. Instead, you might notice something closer to a single, connected system, where changes in one part of the world quietly echoed across the rest. This is the idea of a unified Earth, a time when climate was not something you could point to on a regional map, but something that belonged to the planet as a whole. To understand how that could even be possible, it helps to set aside the way we usually think about weather and climate. Today we're used to hearing about local forecasts, regional droughts, polar ice melt and tropical storms, each tied to a specific place. These things feel separate, as if they belong to different stories happening at the same time. But beneath all of that is a single, continuous layer of air and water that wraps around the globe. The atmosphere doesn't stop at national borders, and the oceans don't pause at coastlines. They move, circulate, and exchange energy in ways that link distant places together, whether we notice it or not. In the deep past, those links may have been even stronger. The surface of the planet looked very different. Mountain ranges were lower or not yet formed. Ice caps, when they existed at all, waxed and waned in ways that didn't resemble our modern polar regions. The continents themselves were often clustered together or arranged in unfamiliar patterns, leaving vast, open stretches of ocean. All of these factors mattered because they shaped how air and water moved. Air moves because of differences in temperature and pressure. Warm air rises, cool air sinks, and the planet's rotation bends those movements into large looping currents. On today's Earth, those loops are broken up by landforms and temperature contrasts. The Himalayas deflect winds. The Sahara heats the air above it. The Antarctic ice cap chills the southern atmosphere. Each of these features helps carve the global circulation into smaller, more localized systems. Imagine instead a world without those sharp contrasts. Picture continents that are lower and smoother, oceans that stretch across most of the surface, and temperature differences between equator and pole that are gentler. In that kind of setting, the great atmospheric loops could grow wider and more continuous. Rather than breaking into distinct cells that dominate certain latitudes, the circulation might feel more like a single, slow-turning engine, drawing energy from the sun and redistributing it around the planet in broad sweeps. The oceans would have played a similar role. Water absorbs heat, holds onto it, and releases it slowly. This is why coastal regions today often have milder climates than inland areas. In the past, when oceans covered even more of the surface and land barriers were fewer, this moderating influence could extend farther. Currents could travel long, uninterrupted paths, carrying warmth from sunlit regions toward cooler ones, and returning cooler water back again. The result would be a more even distribution of heat across the globe. This doesn't mean every place would feel identical. Even in a unified system, there would still be variation. Some regions would receive more sunlight simply because of their position on the sphere of the planet. Others would still be influenced by local features, like shallow seas or clusters of islands. But the overall character of the climate would be shaped less by local quirks and more by the behaviour of the planet as a whole. There's another layer to this story, one that lives high above the surface, in the chemistry of the atmosphere itself. The mix of gases in the air acts like a set of controls on the planet's temperature. Carbon dioxide, methane, and water vapour trap heat, while other components allow it to escape back into space. In the early Earth, the balance of these gases was very different. Oxygen was scarce, carbon dioxide was abundant. Methane, produced by early life and geological processes, likely played a significant role in warming the planet. When these gases are spread evenly around the globe, they create a kind of planetary thermostat. Heat absorbed in one region isn't easily lost to space without passing through this shared atmospheric layer. Instead, it tends to be redistributed, smoothing out extremes. In a world with fewer disruptions to circulation, this effect would be even more pronounced. The atmosphere becomes not just a blanket over each region, but a single, continuous envelope that belongs to the planet as a whole. Thinking about climate in this way can feel a bit abstract, so it helps to bring it back to something more familiar. Consider a large room with a heater in one corner and a fan in the middle. If the room is full of furniture, walls and partitions, the warm air will get trapped in some areas and cool air will linger in others. You'll have pockets of different temperatures, but if you remove most of those obstacles, the fan can circulate the air more freely. Over time, the temperature evens out. The whole room starts to feel like it shares the same air. Early Earth, in many ways, may have been more like that open room than the partitioned one we live in today. The barriers that now shape and separate climate zones were either smaller, arranged differently, or absent altogether. This allowed the atmosphere and oceans to act more like global mixers, blending heat, moisture, and energy across vast distances. Geological evidence gives us hints that this kind of planetary behaviour really did occur. Scientists study ancient rocks, not just for what they're made of, but for the chemical fingerprints they carry. Certain elements and isotopes form or change in predictable ways depending on temperature, the presence of water, and the composition of the atmosphere. When similar signatures appear in rocks from places that are now very far apart, It suggests that those regions once shared similar environmental conditions. For example, there are layers of rock known as banded iron formations that appear in many parts of the world and date back to roughly the same period in Earth's history. These formations tell a story about the chemistry of the oceans and atmosphere at the time, particularly the rise of oxygen. The fact that they appear globally hints at changes that weren't confined to a single basin or coastline, but affected the planet's systems as a whole. Glacial deposits provide another clue. There are places near today's equator where rock shows signs of having been shaped by ice long ago. Scratches in stone, certain types of sediment, and the arrangement of mineral grains all point to the movement of glaciers. Finding this evidence in what are now tropical regions suggests that, at certain times, cold conditions extended far beyond the poles. That kind of widespread glaciation would require a climate system that was operating on a planetary scale. When you put these pieces together, a picture starts to form. Not a detailed, high-resolution image, but a broad, impressionistic one. It shows a world where the major shifts in temperature, chemistry, and circulation didn't just affect one region at a time. They swept across the globe, changing conditions everywhere in a connected way. This connectedness also helps explain how the planet could move from one extreme state to another. A unified system can amplify changes. If something begins to cool the planet, like a drop in greenhouse gases, or a shift in how much sunlight is reflected back into space, that cooling can spread through the global circulation. As temperatures fall, ice forms. Ice reflects more sunlight, which leads to more cooling, which leads to more ice. The feedback loop doesn't stay local. It becomes planetary. The same is true in the other direction. If something begins to warm the planet, like an increase in volcanic carbon dioxide, that warmth can be carried around the globe by air and water. Ice melts, darker surfaces are exposed, more sunlight is absorbed, and the warming accelerates. Again, the response isn't confined to one area. It becomes part of a global shift. There's something almost quiet and steady about this process when you think about it on geological timescales. These changes don't happen overnight. They unfold over thousands or millions of years. From a human perspective, that's unimaginably slow. From the planet's perspective, it's just the way things move. The unified climate isn't a single moment frozen in time. It's a phase in a long, ongoing process where the whole system leans in one direction or another. Life, emerging and evolving within the system, would have experienced the world very differently than we do. Early organisms didn't have to adapt to sharply contrasting climates, separated by oceans or mountain ranges. Instead, they lived in a world where conditions changed gradually across space and time. This may have allowed life to spread more easily, carried by currents and winds that connected distant parts of the planet. At the same time, a unified climate could also mean that when things went wrong, there was nowhere to hide. If the planet cooled or warmed dramatically, every ecosystem felt the effects. Survival depended not on moving to a different climate zone, but on adapting to the new global conditions. This kind of pressure can drive major changes in life, pushing evolution in new directions. There's an interesting parallel here with how we think about Earth today. Even though we talk about local impacts of climate change, scientists often emphasize that it's a global problem. Greenhouse gases released in one place mix into the atmosphere and affect temperatures everywhere. Melting ice in one region can influence sea levels around the world. Changes in ocean currents can alter weather patterns on distant continents. In a sense, we're being reminded that, at a fundamental level, Earth's climate system is still unified. We just happen to live in a phase where its local expressions are more pronounced. Returning to the deep past, the idea of a unified Earth also invites us to think differently about the concept of normal. It's easy to assume that the climate patterns we grew up with represent some kind of stable baseline, but the planet's history shows a series of very different baselines, each lasting millions of years. A world wrapped in ice, a world thick with greenhouse gases, a world with high seas and low continents. Each of these states had its own version of a global system, its own way of balancing energy and matter across the surface. In that sense, the unified climate isn't a single, specific condition. It's more like a mode of operation. It describes a time when the dominant forces shaping temperature, circulation, and chemistry worked at the scale of the whole planet, rather than being broken into many semi-independent regional systems. As you sit with this idea, it can be helpful to think about how rarely we get to experience anything truly global in our daily lives. Most of what we notice is local. The weather outside your window, the temperature of the room you're in, the season in your part of the world. And yet, above and around all of that, the atmosphere is constantly moving, carrying traces of distant places. Dust from one continent can fall as rain on another. Smoke from a wildfire can drift across oceans. A change in ocean temperature in one region can influence storms thousands of kilometers away. Those are small, everyday reminders of a deeper truth. The planet is, and always has been, a single, connected system. The unified Earth of the past simply made that connection more visible in the way its climate behaved. There's a gentle shift that happens when you start to see the world this way. The idea of here and there becomes a little softer. The air you're breathing has been somewhere else. The water in your glass has been part of clouds, rivers and oceans far beyond your view. Even the warmth you feel from the sun is part of a flow of energy that touches every part of the planet, whether it's reflected by ice, absorbed by forests, or stored in the depths of the sea. From that perspective, the story of a unified climate isn't just about ancient history, it's also about a way of seeing. It invites you to imagine Earth not as a collection of separate places, but as a single, continuous environment shaped by forces that don't recognize borders or categories. Long before anyone ever checked a forecast, marked a calendar, or felt the quiet relief of knowing spring was on its way, there was an Earth that didn't yet understand what a season was. The familiar rhythm of warming and cooling, of leaves budding and falling, of snow giving way to rain simply didn't exist in any recognizable form. Instead, the planet moved through time under a sky that was still finding its voice, an atmosphere that was less a finished system and more an ongoing experiment, shaped by deep forces rising from below and distant light pouring in from above. To picture this world, it helps to let go of the colours and textures we usually associate with Earth. There were no green forests swaying in the wind, no wide fields of grass, no birds tracing arcs across a blue sky. The land was mostly bare rock, shaped by heat, water, and the slow grind of geological movement. The oceans were already there, vast and restless. But their chemistry was different, often tinted with dissolved minerals and metals that would look strange to modern eyes. And above it all hung an atmosphere that was thick, heavy, and alive with gases that today play only minor roles in the air we breathe. The earliest atmosphere Earth ever had didn't last very long. When the planet first formed, it likely captured a thin veil of hydrogen and helium from the cloud of gas that surrounded the young sun. But Earth's gravity wasn't strong enough to hold on to those light gases for long. They drifted off into space, leaving the planet to build a new atmosphere from scratch. That new sky came from within. Volcanoes were the architects of this second atmosphere. As the planet's interior churned and melted, gases trapped in rock were released into the air. Water vapour, carbon dioxide, nitrogen, sulfur compounds, and traces of other gases poured out through countless eruptions across the surface. Over time, these emissions accumulated, forming a thick cloudy blanket around the planet. Water vapour condensed and fell as rain, filling the basins of the young oceans. Carbon dioxide stayed in the air, helping trap heat. Nitrogen built up as a stable background gas, forming the bulk of the atmosphere, much as it does today. The result was a sky that was dense, hazy, and far removed from the clear oxygen-rich air we now take for granted. In this early world, the idea of a season didn't make much sense. Seasons, as we know them, depend on a few key ingredients: One is the tilt of Earth's axis, which changes how sunlight is distributed across the planet over the course of a year. Another is the presence of land, ice, and vegetation that respond to those changes in sunlight by heating, cooling, growing, or shedding. But on a young Earth, those surface features were either absent or very different. There were no vast ice sheets to grow and shrink with the changing angle of the sun. The continents, if they existed as large, stable landmasses at all, were smaller and often clustered together. The oceans covered much of the surface, and water, unlike land, doesn't heat up and cool down quickly. It absorbs and releases heat slowly, smoothing out temperature swings. This alone would have made the planet's climate feel more even throughout the year. The atmosphere itself also played a role. With higher concentrations of greenhouse gases, the planet retained more of the sun's energy. This helped keep temperatures relatively stable, even as the amount of sunlight hitting different parts of the globe shifted slightly over the course of an orbit. Instead of sharp seasonal contrasts, the world may have experienced long periods of similar conditions, punctuated by slow, subtle changes rather than dramatic transitions. The sun, too, was a different presence in the sky. Early in its life, our star was dimmer than it is now. This is part of what scientists call the faint young sun paradox. Based on the sun's output alone, Earth should have been frozen solid for much of its early history. But geological evidence shows that liquid water existed on the surface, which means the planet must have had a way to stay warm. The answer, once again, points to the atmosphere. Carbon dioxide and methane, both powerful greenhouse gases, were likely far more abundant. Methane, in particular, may have been produced by some of the earliest forms of life, tiny microorganisms that thrived in the absence of oxygen. These gases formed a thick insulating layer, trapping heat and offsetting the weaker sunlight. The result was a kind of global balancing act, where the atmosphere compensated for the sun's lower output. This balancing act wasn't static. It shifted over time as volcanic activity waxed and waned, as chemical reactions between the atmosphere, oceans and rocks removed or released gases, and as life itself began to influence the composition of the air. The sky above the young Earth was, in a very real sense, a work in progress. One of the most dramatic moments in this atmospheric story came with the rise of oxygen. For a long time, free oxygen was almost non-existent in the air. It was a reactive gas, quickly binding with metals and other elements at the surface. But as photosynthetic organisms, particularly early forms of cyanobacteria, began using sunlight to split water molecules and release oxygen as a byproduct, the balance slowly began to change. At first, the oxygen didn't build up in the atmosphere. It was absorbed by the oceans and the land, reacting with dissolved iron and other substances. This process left behind those banded iron formations that geologists still study today, layers of rock that record the gradual saturation of the planet's ability to soak up oxygen. Only after these sinks were filled did oxygen begin to accumulate in the air. When it did, the atmosphere entered a new phase of its experiment. Oxygen changed the chemistry of the sky, the oceans and the land. It allowed for the formation of an ozone layer high in the atmosphere, which began to block some of the sun's harmful ultraviolet radiation. This, in turn, made it easier for life to spread into new environments, including shallow waters and eventually the surface of the land. But in terms of climate, the rise of oxygen also meant a shift in the greenhouse balance. Oxygen itself is not a greenhouse gas, but its presence affected the abundance of others. Methane, for example, reacts with oxygen and breaks down. As oxygen levels rose, methane levels likely fell, reducing the planet's ability to trap heat. This may have contributed to some of the global cooling events that led to widespread glaciation. Through all of this, the atmosphere remained a global system. Gases released in one place mixed into the air and spread around the world. Changes in composition didn't stay local for long. Over time, they altered the climate everywhere. Without the strong seasonal signals we experience today, the ancient Earth's climate was shaped more by these long-term, planet-wide shifts than by the yearly cycle of sunlight. Instead of thinking in terms of summers and winters, it makes more sense to think in terms of eras, long stretches of time when the world was warmer, followed by periods when it was cooler, phases when ice advanced across large portions of the surface, and phases when it retreated, revealing rock and ocean once more. The oceans were deeply involved in these changes. They acted as both a reservoir and a mediator. Carbon dioxide dissolved in seawater, forming carbonic acid and contributing to the weathering of rocks on the seafloor and along coastlines. This process slowly removed carbon from the atmosphere, cooling the planet. At the same time, volcanic activity returned carbon dioxide to the air, warming it again. This slow exchange created a feedback loop that helped regulate the planet's temperature over immense spans of time. In a world dominated by ocean, this loop had a global reach. There were fewer isolated basins or landlocked seas where conditions could diverge significantly from the rest of the planet. Water masses could circulate more freely, carrying heat and dissolved chemicals across great distances. This helped maintain a sense of planetary coherence in the climate system. It's also worth considering the role of clouds. Even today, clouds are one of the most complex and uncertain parts of climate science. They can both cool the planet by reflecting sunlight and warm it by trapping heat. On the ancient Earth, with a different mix of atmospheric gases and possibly higher levels of particles from volcanic eruptions, cloud formation may have followed different patterns. Thick, widespread cloud cover could have further smoothed out temperature differences, contributing to a more uniform climate. All of these factors together created a world where the atmosphere was not just a passive backdrop, but an active participant in shaping conditions at the surface. It was constantly being built up, broken down and rebuilt again, driven by forces from the planet's interior, the chemistry of its oceans, the activity of its earliest life, and the steady, patient energy of the sun. From a human perspective, it's hard to fully grasp what it would be like to live in such a world. We're so accustomed to the idea that the year is divided into parts, that certain months mean certain things, that the weather follows a rough script we can plan around. But on the ancient Earth, time didn't announce itself that way. Change came slowly, almost imperceptibly from one generation to the next, but dramatically over the span of millions of years. If you were a simple organism drifting in those early oceans, you wouldn't notice a season turning. You might notice that the water was on average a little cooler than it had been long ago, or that the chemistry of your surroundings was gradually shifting. These were the signals of climate in a world without calendars, without the fast repeating cycle of seasons to mark the passage of time. There's something quietly fascinating about that. Climate as a deep, slow pulse rather than a quick, familiar rhythm. The planet breathing in and out over geological time rather than day by day. As the atmosphere continued its long experiment, the surface of the Earth changed with it. Continents grew larger and more defined. Mountain ranges rose where plates collided, introducing new barriers to the flow of air and water. Ice caps began to form at the poles during cooler periods, reflecting sunlight and strengthening temperature contrasts. Vegetation eventually spread across the land, altering how much heat the surface absorbed and how much moisture was returned to the air. These developments didn't happen all at once. They accumulated layer by layer, era by era. But their combined effect was to give the planet more texture, more variation. The once smooth, global patterns of circulation began to break into smaller, more localized systems. The seeds of seasons, as we know them, were being planted. Still, in this earlier phase, before those features took hold, the atmosphere was free to act on a grand scale. Its experiments weren't about fine-tuning local weather. They were about finding a balance for the planet as a whole. How much heat to keep, how much to let go, which gases would dominate, how life and rock and water would interact under a shared sky. There's a quiet continuity between that ancient world and the one you're in now. The air around you is still part of the same system, even if its composition and behaviour have changed. The carbon dioxide you exhale will eventually mix into the global atmosphere. The warmth from the sun still drives the movement of air and water around the planet. The feedback loops between rocks, oceans and sky are still turning, just on timescales that stretch far beyond a human lifetime. Thinking about the ancient Earth's first atmospheric experiments can feel like looking at the opening pages of a very long book. The characters and settings are different, but the themes are already there. Balance and imbalance, connection and change. The way small processes, repeated over and over, can reshape an entire world. At the very beginning of this part of the journey, it helps to imagine not the land beneath your feet, but the water that would have surrounded it, stretched far beyond any horizon you could reach. Picture a world where the oceans were not divided by familiar coastlines or hemmed in by the recognizable shapes of continents, but instead formed a near-continuous skin of moving, breathing water wrapped around the planet. In that setting, the seas were less a collection of separate bodies and more a single connected system, flowing in slow, patient patterns that linked one side of the Earth to the other. Water, more than almost anything else on the planet, is a great unifier. A drop that falls as rain in one place can, over time, find its way into a river, then into the ocean, and eventually be carried by currents across thousands of kilometers before rising again into the air as vapor. Even today, the oceans operate as one global body, stitched together by deep and surface currents that move heat, salt, and nutrients around the world. In the deep past, when the arrangement of land was simpler and the barriers fewer, that sense of connection may have been even stronger. The earliest oceans formed as the planet cooled, and water vapour in the atmosphere condensed and fell as rain. This wasn't a gentle drizzle. For long stretches of time, the sky likely released water in torrential downpours, filling basins, covering low-lying land, and carving channels into the bare rock. Over millions of years, these rains built vast, deep bodies of water that became the dominant feature of the surface. In some eras, oceans may have covered more than 70% of the planet, leaving only scattered land masses breaking the surface like islands in a global sea. With so much of the world covered in water, the oceans took on a central role in shaping the planet's climate. Water has a remarkable ability to store heat. It warms up slowly, cools down slowly, and holds onto energy long after the source of that energy has changed. This makes the ocean a kind of thermal memory for the planet, absorbing sunlight near the equator and releasing that heat gradually as water moves toward cooler regions. On a young Earth with fewer large continents and lower mountain ranges, there were fewer obstacles to block this movement. Currents could follow long, looping paths, driven by differences in temperature, salinity, and the gentle pull of the planet's rotation. Instead of being deflected or split by narrow straits and sprawling land masses, these flows could circle much of the globe, linking distant regions in a shared rhythm of motion. To get a sense of how powerful this can be, it's worth looking at what happens today. The modern ocean circulation system, often called the global conveyor belt, moves water through a network of surface and deep currents that span the entire planet. Warm, salty water flows from the tropics toward the poles near the surface, while cold, dense water sinks and travels back toward the equator in the deep ocean. This process helps regulate climate by transferring heat from where it is abundant to where it is scarce. Now imagine that system in a world where the pathways were even more open. Fewer continental barriers would mean longer, more continuous routes for both surface and deep currents. The ocean could act as a more unified engine, smoothing out temperature differences on a planetary scale. Regions that might otherwise cool rapidly would receive a steady supply of warmth, carried by water from sunnier latitudes. Areas prone to overheating would be moderated by cooler water flowing in from elsewhere. This kind of circulation would give the planet's climate a different character. Instead of sharp boundaries between warm and cold zones, there could be broader gradients, more gradual transitions from one region to another. The ocean's steady hand on the temperature dial would make the world feel more consistent, more connected, as if the same underlying pattern was playing out everywhere, just with small variations. The chemistry of the early oceans also added another layer to this shared rhythm. These waters were rich in dissolved minerals and gases, many of them released from the planet's interior through volcanic activity. Iron, sulfur, carbon compounds and other elements were present in forms that are rare or absent in today's oxygen-rich seas. As water circulated around the globe, it carried these substances with it, mixing them and distributing them across vast distances. This mixing had consequences not just for climate, but for life. Early organisms depended on the chemical makeup of their surroundings. Nutrients dissolved in seawater were their building blocks, their sources of energy, their pathways to survival. A more unified ocean system meant that these resources could be spread more evenly around the planet. Life that emerged in one region could, over time, find similar conditions elsewhere, carried along by currents or supported by the global circulation of key elements. Temperature and chemistry weren't the only things moving through this ancient ocean. The water itself was in constant conversation with the atmosphere above. Gases dissolved into the sea and were released back into the air. Carbon dioxide, in particular, played a crucial role. When it entered the ocean, it formed carbonic acid, which could react with rocks on the seafloor or along coastlines, locking carbon away in solid form. This process helped draw down the amount of carbon dioxide in the atmosphere, cooling the planet over long periods of time. At the same time, volcanic eruptions and the slow movement of tectonic plates brought carbon back to the surface, releasing it into the air once more. The oceans, acting as an intermediary, were part of this grand, slow cycle that helped regulate the planet's temperature. In a world where the seas were more continuous and circulation more global, this regulatory system would have operated on a planetary scale, reinforcing the idea of a shared climate. Another important feature of the early oceans was their depth. Without large ice caps to lock water away on land, sea levels were often higher. Shallow seas flooded continental margins, creating vast sunlit shelves where water, light and minerals came together. These areas were especially important for life, providing environments where early organisms could thrive and spread. These shallow regions weren't isolated pockets. They were connected by the same water that filled the deep basins and wrapped around the planet. Currents moved through them, bringing in fresh supplies of nutrients and carrying away waste products. The boundary between one ocean and another was less defined than it is today. Instead of thinking in terms of separate basins, it makes more sense to picture a single, global ocean with different faces and depths, all linked by motion. Light, too, played its part in shaping this shared rhythm. Sunlight penetrates only the upper layers of the ocean, but those layers are where much of the interaction between water, air and life takes place. The warmth from the sun heats the surface, creating differences in temperature and density that help drive circulation. In a world with fewer shadows cast by continents and ice, the pattern of sunlight across the ocean would have been smoother, reinforcing the broad planetary nature of these flows. Storms and winds generated by the movement of air above transferred energy to the water below. Waves travelled across open stretches of ocean without interruption, carrying momentum and mixing surface layers. The wind-driven currents they helped create could extend for thousands of kilometres, connecting distant regions through a shared pattern of motion. If you were to stand on a piece of land in that ancient world and look out across the water, the view might not have hinted at any of this. You would see waves breaking at the shore, clouds reflected in the surface, perhaps a horizon that felt endless. But beneath that surface, a slow, steady movement was tying your location to places you could never see. Warm water from far away might be passing by below you. Dissolved minerals from distant volcanic eruptions could be flowing through the currents. The ocean was quietly stitching the planet together. There's also evidence locked in the rocks that supports this idea of a connected sea. Marine sediments from different parts of the world show similar chemical signatures from the same periods in Earth's history. This suggests that the conditions in the oceans were not wildly different from place to place, but shared certain global characteristics. Isotopes of elements like carbon and oxygen can reveal information about temperature and the composition of seawater at the time those sediments formed. When those signals line up across continents, it points to changes that affected the oceans as a whole. One striking example comes from periods of widespread glaciation. As ice formed on land, sea levels dropped, exposing parts of the seafloor. At the same time, the temperature and chemistry of the oceans changed. These shifts are recorded in layers of sediment found in many regions. The fact that they appear globally indicates that the ocean responded as a single system to changes in climate, rather than as a set of isolated basins. The idea of oceans without borders isn't just about physical connection, it's also about timing. The movements of water operate on timescales that can be both fast and slow. Surface currents can carry water across an ocean basin in years or decades. Deep currents, driven by the sinking of cold, dense water at high latitudes, can take centuries or even millennia to complete their circuits. In the ancient world, these deep flows would have been part of the planet's long-term memory, carrying the imprint of past conditions forward through time. This means that a change in one part of the world didn't just affect that place in the moment. Its influence could be carried along by the ocean, slowly, quietly, shaping conditions elsewhere long after the initial cause had faded. A burst of volcanic activity in one region could alter the chemistry of seawater that would eventually reach the other side of the planet. A period of cooling at high latitudes could send a pulse of cold, dense water into the deep ocean that would take centuries to spread. There's something almost meditative about thinking of the ocean in this way, not as a restless, chaotic surface of waves and storms, but as a deep, slow-moving system that holds on to the past and carries it forward. In a unified climate, this kind of memory would have helped keep the planet in a particular state for long stretches of time. The ocean would reinforce whatever balance the system had found, whether that balance leaned toward warmth or cold. As continents grew and shifted, this open global sea began to change. Land rose from the water, dividing basins and redirecting currents. Narrow passages formed between continents, speeding up flows in some places and blocking them in others. The once broad, looping paths of circulation were broken into more complex networks. Regional patterns began to emerge, and with them, more localized climates. But before that happened, the ocean's role as a planetary connector was likely more pronounced. It was the main stage on which the Earth's unified climate played out, carrying energy, chemicals, and life itself across the surface in a shared, global motion. There's a quiet connection between that ancient ocean and the one we know today. The water in the seas right now is part of the same cycle. Molecules of H2O that were present billions of years ago are still moving through the system, passing from ocean to atmosphere to land and back again. The currents that circle the globe now are descendants of those early flows, shaped by a planet that has changed its face many times but never lost its fundamental connection between water, air, and energy. As you consider this, it might be interesting to think about the water you interact with every day, the glass you drink from, the rain that taps against a window, the mist that rises from a river in the morning. All of it is part of this larger story, a tiny piece of a global system that has been moving, mixing and circulating since the earliest days of the planet. The oceans without borders of the deep past remind us that Earth's climate has always been more than a collection of local conditions. It's a planetary process, one that flows through water and air, rock and life, connecting distant places in ways that aren't always visible on the surface. Far above the slow turning of oceans and the quiet shifting of continents, there was another presence shaping the planet in a way that was both constant and ever-changing at the same time. It didn't rumble like a volcano or flow like a current. It didn't leave behind rocks or sediments for future scientists to study. Instead, it arrived silently, moment after moment, as a steady stream of energy crossing the emptiness of space and settling onto the surface of the Earth. This was the sun, and in the deep past its role in guiding the planet's balance was both simpler and more profound than it often feels today. To think about ancient sunlight, it helps to move beyond the idea of a warm day or a bright sky. What the sun really provides is energy, and energy is what drives almost everything that happens in a climate system. It warms the air, heats the water, powers the winds, and fuels the slow chemical reactions that shape the atmosphere and the surface of the planet. Even the movement of ocean currents, which feel so grounded in the physical world, ultimately traces back to the uneven heating of the Earth's surface by sunlight. Early in Earth's history, the sun was not quite the star we know now. Stars, like all things, change over time. When our sun was young, it was slightly dimmer, producing less energy than it does today. This seems like a small detail, but over the scale of an entire planet, it makes a meaningful difference. Less incoming energy should, in theory, lead to a colder world. And yet, the geological record tells us that the early Earth was not a frozen sphere. Liquid water flowed across its surface, oceans existed, life found a foothold. This apparent contradiction, often called the faint young sun problem, points directly to the way sunlight and the planet's own systems work together to create a balance. The sun provided the energy, but the atmosphere and oceans decided how much of that energy stayed and how much was sent back into space. The key players in this balancing act were the gases in the atmosphere. Carbon dioxide, methane and water vapour are all capable of absorbing and re-emitting infrared radiation, the form of energy that the Earth gives off after being warmed by the sun. By doing this, they act like a thermal blanket, trapping heat close to the surface. In the ancient atmosphere, these gases were present in much higher concentrations than they are now. Volcanoes continuously released carbon dioxide into the air. Early microbial life, thriving in environments without oxygen, produced methane as a byproduct of their metabolism. Water vapour, always present over warm oceans, added to the mix. Together, these gases formed a thick insulating layer that compensated for the sun's lower output. In effect, the planet adjusted itself. The sun delivered less energy, but the atmosphere held onto more of what it received. This allowed temperatures to remain within a range that supported liquid water and the chemical processes essential for life. It's an early example of what scientists now call a feedback system, where different parts of the planet interact in ways that tend to stabilize overall conditions. But this balance was not fixed. It shifted over time as both the sun and the Earth changed. The sun very slowly grew brighter as it aged. Deep within its core, hydrogen was being fused into helium, altering the internal structure of the star and increasing its energy output. This process takes billions of years, but its effects accumulate. A slightly brighter sun means more energy reaching the Earth's surface. At the same time, the planet's ability to trap that energy evolved. As oxygen began to build up in the atmosphere, methane levels dropped, because methane reacts with oxygen and breaks down. This reduced the strength of the greenhouse effect. Meanwhile, carbon dioxide was being drawn out of the air through chemical reactions with rocks and sediments, a process tied to the slow movement of water across the land and sea floor. These changes meant that the planet was constantly adjusting to a moving target. The sun was getting brighter. The atmospheric blanket was, in some periods, getting thinner. The result was a climate system that had to keep finding new points of balance. One of the most striking ways this played out was in the shifting boundaries between warm and cold regions. Sunlight doesn't fall evenly across a sphere. The equator receives more direct, concentrated energy, while the poles receive sunlight at a lower angle, spread out over a larger area. This basic geometry creates a natural tendency for the equator to be warmer than the poles. On a modern Earth, that difference is reinforced by ice caps at the poles. Ice reflects a large fraction of incoming sunlight back into space, keeping those regions cold. Vegetation and darker surfaces near the equator absorb more sunlight, warming the air and the ground. This contrast helps drive strong atmospheric circulation, creating distinct climate zones. In the ancient world, the picture may have been different. With fewer large ice caps and different land arrangements, the contrast between equator and pole could have been smaller. The sun still delivered more energy to the tropics, but the way that energy was stored and moved around by the oceans and atmosphere may have smoothed out the differences. If the poles were warmer than they are today, even by a few degrees, the global circulation would take on a different character. Winds might follow broader, slower paths. Storm systems could be less tightly confined to specific latitudes. The planet's climate would feel more unified, shaped by a global pattern of energy flow rather than a patchwork of sharply defined zones. Sunlight also influenced the chemistry of the atmosphere in direct ways. High-energy ultraviolet radiation from the sun can break apart molecules, a process known as photodissociation. In the early atmosphere, this played a role in shaping the abundance of gases like water vapour, methane and carbon dioxide. When water vapour is broken apart, for example, the lighter hydrogen can escape into space, while the heavier oxygen remains behind. Over immense spans of time, this process contributed to the gradual loss of hydrogen from the atmosphere and the accumulation of oxygen. This means that the sun wasn't just warming the planet, it was actively participating in the evolution of the sky itself. The light that reached the upper atmosphere was helping determine which gases stayed, which changed form, and which drifted away. In a sense, ancient sunlight was writing part of the chemical story of the Earth. The oceans felt this influence as well. Sunlight penetrates the upper layers of water, warming the surface and creating differences in temperature between shallow and deep regions. This temperature difference affects density, which in turn drives vertical movement in the ocean. Warm water tends to stay near the surface, while cooler, denser water sinks. This vertical mixing is a key part of how nutrients are brought up from the depths and how heat is transported downward. In a world where sunlight patterns were smoother and ice cover was less extensive, this mixing could have been more uniform across large areas of the ocean. Instead of strong, localized upwelling zones and sharply defined thermal layers, there may have been broader regions where surface and deep waters exchange properties more gradually. This would further contribute to the sense of a shared planetary rhythm in the climate system. There's also the matter of day and night. The length of Earth's day has not always been what it is now. Early in the planet's history, it rotated faster. Days were shorter. Over time, interactions with the moon have slowed the rotation, lengthening the day to its current 24 hours. Shorter days mean that any given spot on the surface spends less time in sunlight and less time in darkness during each rotation. This has subtle effects on how heat is absorbed and released. With faster rotation, the surface doesn't have as much time to heat up under the sun or cool down under the night sky before conditions change again. This can lead to more even temperatures over the course of a day. When combined with the ocean's ability to store heat and the atmosphere's ability to move it around, this could make the planet's climate feel even more uniform. Thinking about ancient sunlight in this way highlights how many layers of influence it had. It wasn't just a lamp in the sky, it was a driver of physical movement, a trigger for chemical reactions, and a quiet partner in the long conversation between the Earth's surface, its oceans, and its atmosphere. Over time, as the sun grew brighter, the planet's systems responded. One of the most important responses involved the weathering of rocks on land. When rain falls, it reacts with carbon dioxide in the air to form a weak acid. This acid slowly dissolves certain minerals in rocks, a process that locks carbon away in solid form. Rivers carry these dissolved materials to the ocean, where they can eventually become part of sediments on the seafloor. This is another feedback loop. More sunlight means warmer temperatures. Warmer temperatures can lead to more rainfall. More rainfall means faster weathering. Faster weathering removes more carbon dioxide from the atmosphere. Less carbon dioxide means a weaker greenhouse effect, which can counteract the warming from the brighter sun. In this way, ancient sunlight and ancient rock were linked in a slow planetary dialogue. The sun pushed the system in one direction. The Earth's surface processes pushed back, helping maintain a balance that kept conditions within a range that allowed oceans to remain liquid and life to continue. There were times when this balance was disrupted. Periods of intense volcanic activity could release large amounts of carbon dioxide, strengthening the greenhouse effect and leading to warmer global temperatures. On the other hand, times when continents were positioned in ways that increased weathering, such as when large land masses lay in warm, wet regions, could draw down carbon dioxide and cool the planet. In each case, the sun remained the steady source of energy in the background. The planet's response to that energy determined how warm or cool the surface became. Another way to think about this is in terms of contrast. Today, much of the drama in Earth's climate comes from differences. Differences between land and sea, differences between ice and open water, differences between forest and desert. These contrasts shape how sunlight is absorbed or reflected, and they create the complex patterns of heating that drive regional climates. In the deep past, some of those contrasts were less pronounced. With fewer large land masses and less ice, the surface may have had a more uniform ability to absorb sunlight. Dark ocean water absorbs a lot of energy. Bare rock absorbs less than water, but more than ice. If much of the planet was covered in ocean or similar surfaces, the way sunlight was handled at the surface would be more consistent from place to place. This doesn't mean the world was flat or featureless, but it does suggest that the big, dramatic differences we're used to now were still in the process of developing. The sun's energy fell on a planet that responded in a more globally coordinated way, reinforcing the idea of a unified climate system. It's also worth remembering that the sun itself isn't perfectly constant. It goes through cycles of activity, with periods of higher and lower output, sunspots and solar flares. On human timescales, these variations are relatively small. On geological timescales, their effects are subtle. But in a world where the climate system was more tightly coupled and more sensitive to global changes, even small variations in solar output could have had noticeable effects. A slight dip in energy reaching the surface could encourage ice to expand. A slight increase could promote melting. If the system was already near a tipping point, these gentle nudges from the sun might be enough to push it into a new state. There's something quietly compelling about thinking of the sun as both distant and intimately involved. It sits 93 million miles away, an enormous glowing sphere of plasma, yet its influence is felt in the smallest details of the planet's surface. The warmth on your skin on a clear day is a direct connection to processes happening deep inside that star. The movement of the air around you, the temperature of the water in a lake or ocean, the growth of a plant, all trace back in one way or another to that same source. In the ancient world, that connection was just as real, even if the surface of the planet looked nothing like it does now. The sun's long presence helped shape a climate that was less fragmented, more planetary in scale. Its energy flowed into oceans that carried it across the globe, into an atmosphere that spread it around the world, and into rocks and water that slowly adjusted how much of it was held close and how much was let go. As time went on, the stage began to change. Continents rose higher. Ice began to appear at the poles more regularly. Life transformed the surface, covering it with vegetation that altered how sunlight was absorbed and reflected. These changes introduced new patterns, new contrasts, new ways for the sun's energy to be handled by the planet. But before all of that complexity took hold, there was a simpler, broader relationship. Light from the sun arrived. The planet responded as a whole. Sitting with that idea can feel a bit like stepping back from a detailed painting to see the larger composition. The small, local features blur, and what stands out is the overall flow of light and shadow, warmth and coolness, energy in and energy out. That's the scale at which ancient sunlight operated, guiding the Earth's balance in a way that was less about specific places and more about the planet as a single system. There comes a moment in this long planetary story where the image of a warm, circulating world gives way to something far quieter, far more still. Instead of open water reflecting the sky and winds moving freely across the surface, imagine a planet wrapped in a pale, unbroken shell where the dominant feature is not motion but the absence of it. This is the idea behind what scientists now call snowball Earth, a period, or possibly several periods, in Earth's deep past when ice may have reached from the poles all the way to the equator, turning the world into something that looked less like the blue planet we know and more like a white frozen sphere drifting through space. To understand how such an extreme state could even be possible, it helps to return to the delicate balance we've been tracing between sunlight, atmosphere, oceans and surface. Climate at its core is a negotiation between how much energy comes in and how much goes out. The sun delivers energy. The Earth reflects some of it back into space and absorbs the rest. The atmosphere decides how much of that absorbed energy is held close and how much escapes. In a stable system, these flows are roughly equal over long periods of time, but stability does not mean immobility. The balance can shift, sometimes gradually, sometimes in a way that feels more like a slide down a gentle but persistent slope. Snowball Earth represents a moment when that balance may have tipped far enough toward cooling that the planet entered a self-reinforcing cycle of ice and reflection. The key concept here is albedo, which is a measure of how much sunlight a surface reflects. Dark surfaces like open ocean or bare rock absorb most of the sunlight that hits them. Light surfaces like ice and snow reflect a large portion of it back into space. When a region becomes covered in ice, it stops absorbing heat and starts reflecting it. This makes the area even colder, which allows more ice to form. That, in turn, increases the reflection of sunlight even further. Now, imagine this process not happening in a single region, but spreading across the planet. Ice forms at high latitudes, as it often does during cooler periods. The reflective surface of that ice sends more sunlight back into space, cooling the surrounding areas. As those areas cool, ice begins to form there as well. The boundary between ice and open water slowly creeps toward lower latitudes. With each step, the planet's overall reflectivity increases and the cooling accelerates. This is what scientists call a positive feedback loop. The initial cooling leads to more ice, which leads to more reflection, which leads to more cooling. If this process continues unchecked, it can, in theory, carry the system all the way to a state where most or even all of the surface is frozen. Geological evidence suggests that something like this may have happened several times between about 720 and 635 million years ago. These periods are often referred to as the Sturtian and Marinoan glaciations. The rocks from these times tell a story of cold conditions in places that are now warm. Glacial deposits, which form when ice grinds rock into fine sediment and leaves distinctive patterns behind, have been found in regions that were near the equator at the time these rocks were laid down. This is one of the strongest lines of evidence for a global or near-global glaciation. It suggests that ice wasn't confined to the poles, but extended into tropical latitudes. In other words, the world may have been cold almost everywhere at once. If you pause and try to picture what that would mean for the surface of the planet, the scale of it becomes almost hard to hold in mind. Oceans capped with thick layers of ice, continents buried beneath glaciers, rivers frozen in place. The familiar movement of water, air and life slowed to a near standstill at the surface. Underneath the ice, however, things would not have been entirely silent. The Earth's interior doesn't stop moving just because the surface freezes. Volcanoes would still erupt, releasing heat and gases. The ocean, beneath its icy lid, would still circulate, though in a different way. Life, if it survived, would have done so in pockets where conditions remained tolerable. Perhaps near hydrothermal vents on the sea floor, or in thin layers of water beneath the ice where sunlight could still penetrate. One of the most interesting questions about Snowball Earth is not just how the planet got into such a state, but how it got out. A world covered in ice reflects so much sunlight that it becomes very hard to warm up again. The same feedback loop that drove the planet into deep freeze now works to keep it there. Ice reflects sunlight. Reflection keeps temperatures low. Low temperatures maintain the ice. The escape from this frozen condition likely came from a source that doesn't depend on surface temperature, volcanic activity. As we've touched on before, volcanoes release carbon dioxide into the atmosphere. Normally, this gas is removed over time by processes like weathering, where rain and chemical reactions with rocks draw carbon out of the air and lock it into solid form. But on a frozen planet, those processes slow down dramatically. There is little liquid water flowing over rocks. Weathering nearly grinds to a halt. This means that while carbon dioxide continues to be added to the atmosphere by volcanoes, it is not being removed at the usual rate. Over long periods of time, the concentration of greenhouse gases in the air would build up. The atmospheric blanket would grow thicker and more effective at trapping heat. Eventually, even the highly reflective ice-covered surface would not be able to send enough energy back into space to counteract this growing greenhouse effect. Temperatures would begin to rise. Ice at lower latitudes would start to melt. As soon as patches of dark ocean or land were exposed, they would absorb much more sunlight than the ice ever did. This would create a new feedback loop, this time in the direction of warming. The thaw, once it began, may have been dramatic on a geological timescale. Instead of a slow, gentle retreat of ice, the planet could have experienced a relatively rapid shift from frozen to warm conditions. Oceans would be flooded with meltwater. Rivers would form and reshape the landscape. The atmosphere, thick with carbon dioxide, would drive high temperatures and intense rainfall. In this sense, Snowball Earth represents not just a period of cold, but a kind of climatic pendulum swing. The planet moves to one extreme, then, over time, swings back toward another. Thinking about this in the context of a unified climate, it's striking how global the process appears to have been. The feedback loops involved don't respect regional boundaries. The reflectivity of ice affects the amount of sunlight absorbed by the planet as a whole. The buildup of greenhouse gases in the atmosphere spreads around the globe, influencing temperatures everywhere. The response of the system is planetary in scale. There's something quietly powerful about that idea. It suggests that, at certain moments in its history, Earth behaved less like a collection of separate environments and more like a single, tightly coupled machine. A change in one part of the system didn't stay local for long. It became part of a global shift. Life, caught up in this shift, would have faced immense challenges. A frozen surface world is not a friendly place for most organisms. Photosynthesis, which depends on sunlight, would have been severely limited under thick ice. Nutrient cycles would have been disrupted. Habitats would have shrunk or disappeared. And yet life appears to have survived. This resilience is one of the most intriguing aspects of the Snowball Earth hypothesis. It suggests that even under the most extreme global conditions, there were refuges where organisms could persist. These might have been areas of thin ice near the equator, where sunlight could still reach the water below. They might have been open patches near volcanic regions where heat kept the surface from freezing completely. Or they might have been deep-sea environments, where chemical energy, rather than sunlight, provided the basis for ecosystems. The survival and eventual flourishing of life after these glaciations has led some scientists to wonder whether these extreme events played a role in shaping the course of evolution. The periods following Snowball Earth coincide with the rise of more complex multicellular organisms. It's tempting to imagine that the stress of global freeze and thaw created conditions that favoured new forms of life, opening ecological space and driving innovation. Returning to the physical side of the story, the evidence for these events is written in layers of rock. In addition to glacial deposits, scientists find distinctive layers of sediment that form in warm, carbonate-rich oceans. These cap carbonates often sit directly on top of glacial layers. They are thought to represent the aftermath of a snowball Earth, when the planet, freshly thawed and flooded with meltwater, experienced a surge in chemical weathering and mineral deposition. The contrast between the two layers is striking. Below, signs of ice and cold. Above, signs of warm, shallow seas and active chemistry. It's as if the rocks themselves are recording a moment of transition, a line between two very different global states. The idea that the entire planet could flip between such extremes can feel unsettling. We're used to thinking of Earth as stable, reliable, a place where change happens within certain bounds. Snowball Earth reminds us that those bounds are not fixed. The climate system has the capacity, under the right conditions, to move into states that are far outside our everyday experience. At the same time, it also highlights the planet's ability to recover. The same system that allows for dramatic cooling also contains the mechanisms for warming and renewal. Volcanic activity, atmospheric chemistry, and the steady input of solar energy eventually pull the planets back toward conditions that support open water, and with it, more widespread life. There's a kind of slow, geological patience in that process. From a human perspective, a global freeze lasting millions of years is almost unimaginable. From the planet's perspective, it's just another phase in a long sequence of changes. Considering Snowball Earth in the context of oceans without borders and ancient sunlight brings the story full circle. The oceans, once largely open and connected, become sealed beneath ice, their role in moderating climate temporarily suppressed. The sun, still shining as it always has, finds much of its energy reflected back into space by the bright surface. The atmosphere, quietly accumulating greenhouse gases, waits in the background for its chance to tip the balance again. In this frozen world, the sense of a unified climate is taken to its extreme. There are no warm tropics and cold poles, no rainy regions and dry ones. The defining feature is cold everywhere. Silence, at least at the surface, becomes the dominant state. Yet even in that silence, the system is not truly still. Beneath the ice, water moves. Beneath the crust, magma flows. Above the surface, the atmosphere slowly thickens with heat-trapping gases. The planet is, in its own way, preparing for the next transition. It's also worth reflecting on how much of this story we've pieced together from small scattered clues. A scratch on a rock face, a layer of sediment in a cliff, the chemical ratio of elements in a sample pulled from deep underground. These fragments, when combined, point to a world-scale event that no human ever witnessed. There's something quietly humbling about that. We live on a planet with a history so vast and dramatic that even its most extreme chapters are reduced to subtle marks in stone, waiting patiently for someone to notice and ask what they mean. Somewhere deep beneath a shell of ice that may have stretched from horizon to horizon, the planet was quietly gathering the conditions for a very different world. Even while the surface lay locked in cold and reflection, the processes that had always shaped Earth were still at work, slow and persistent, almost patient. The Great Thaw is the name often given to the moment when those hidden processes finally tip the balance, and a world that may have been frozen nearly everywhere began to warm, melt, and move again in a way that felt, on a geological scale, almost sudden. To understand how a planet could awaken from such a deep freeze, it helps to return to the idea of climate as a system of flows rather than a collection of places. Heat flows in, energy flows out, gases move between the atmosphere, the oceans, and the rocks. Even when ice covers the surface, these flows do not stop. They simply take different paths. Volcanoes, for example, do not care whether the surface above them is frozen or warm. Deep within the crust and mantle, rock continues to melt, rise, and release gases. Carbon dioxide is one of the most important of those gases for climate because of its ability to trap heat. During a global glaciation, the usual ways that carbon dioxide is removed from the atmosphere slow down dramatically. Rainfall is limited, rivers are frozen or absent. Chemical reactions between water and rock that would normally draw carbon out of the air and lock it into minerals happen far less often. This creates a kind of imbalance. Carbon dioxide continues to be added to the atmosphere by volcanic activity, but it is not being removed at the same rate. Over hundreds of thousands or even millions of years, the concentration of this greenhouse gas builds up, layer by layer, molecule by molecule. At first, the thick ice covering the planet reflects most of the sunlight back into space, and the surface remains cold. But as the atmospheric blanket grows stronger, more of the heat that does make it through the reflective shell is trapped. The system begins to lean, very gradually, toward warming. There isn't a single moment you could point to and say, this is when the thaw began. Instead, it's more like watching a block of ice on a cold day, as the temperature slowly rises. At first, nothing seems to change. The surface stays solid. The edges are sharp. Then, at some point, you notice a thin film of water forming. A drop appears. The change, once it starts, becomes easier to see. On a planetary scale, that first hint of thaw may have appeared at the equator. Even during a snowball Earth, the equatorial regions would have received the most direct sunlight. If the greenhouse effect became strong enough, these areas would be the first to experience melting. Small patches of open water or thinner ice could form, perhaps in long, narrow bands where the sun's energy was most concentrated. Those patches would make a significant difference. Dark, open water absorbs far more sunlight than bright ice. As soon as a bit of the surface shifts from reflective to absorptive, it starts to warm its surroundings. That warmth can spread outward, melting more ice and exposing more dark surface, which in turn absorbs even more energy. This is another feedback loop, but now it runs in the direction of warming rather than cooling. The Great Thaw, in this view, is not a gentle, even retreat of ice. It's a process that can accelerate once it gains a foothold. The first openings in the ice create conditions that make it easier for more openings to form. The system begins to run downhill toward a warmer state. As the ice recedes, the oceans are revealed again. Vast amounts of meltwater pour into them from glaciers and ice sheets, raising sea levels and changing the chemistry of the water. Fresh water is less dense than salt water, so this influx can alter how the ocean circulates, at least for a time. Surface layers become lighter and more buoyant, while deeper layers remain cold and salty. This reawakening of the ocean plays a crucial role in spreading the warming around the globe. Water that absorbs heat near the equator can now move freely toward higher latitudes, carrying that warmth with it. Winds, responding to the changing temperature patterns at the surface, begin to shift and strengthen. Storms return, clouds form. Rain falls on land that may not have seen liquid water for millions of years. The atmosphere itself undergoes a transformation during this period. With high levels of carbon dioxide built up during the frozen phase, the post-thaw world is likely very warm. Some scientists describe it as a kind of hothouse state. Temperatures could rise well above what we would consider comfortable or even survivable in many places today. This warmth drives intense weathering of rocks on land. When rain falls on newly exposed surfaces, it reacts with carbon dioxide in the air to form a weak acid. This acid breaks down certain minerals, drawing carbon out of the atmosphere and carrying it into rivers and eventually the ocean. There, the carbon can become part of sediments on the seafloor. In this way, the thaw sets in motion the very process that will eventually help cool the planet again. The high temperatures and heavy rainfall speed up the removal of greenhouse gases from the air, thinning the atmospheric blanket over time. The climate system begins slowly to move back toward a more moderate state. There's a rhythm to this that feels almost like breathing. The planet takes in carbon through volcanic activity, building up heat-trapping gases. It releases carbon through weathering and sedimentation, letting some of that heat go. During a snowball Earth, the inhale dominates. During the Great Thaw and the warm period that follows, the exhale begins to catch up. Life, if it survived the frozen phase in isolated refuges, would have found this thawing world both challenging and full of opportunity. The return of open water and sunlight would allow photosynthetic organisms to expand. Nutrients released from weathered rocks would wash into the oceans, providing raw material for biological growth. Shallow seas created by rising sea levels would offer wide, sunlit environments where complex ecosystems could develop. There is evidence in the fossil record and in the chemistry of ancient rocks that suggests a burst of biological activity after these global glaciations. This period, often called the Ediacaran, saw the appearance of some of the earliest known complex multicellular organisms. While the exact causes of this evolutionary step are still debated, the dramatic environmental changes associated with the Great Thaw are often considered part of the story. From a climate perspective, what's striking is how coordinated the shift appears to have been. The build-up of greenhouse gases happened globally. The initial melting likely began in specific regions, but once it started, the feedback loops carried the warming across the planet. The reactivation of ocean circulation and atmospheric movement spread heat, moisture, and chemical changes from one region to another. In other words, the thaw was not just a local event repeated many times in different places, it was a planetary transition. The world moved as a system from one state to another. If you imagine standing on the surface during this time, the changes would not feel sudden in any human sense. A glacier retreating by a few meters a year is dramatic on a geological timescale, but over a human lifetime, it might feel almost still. But over thousands of years, the difference would be unmistakable. Places that were once locked in ice would become open water, rock faces would be carved by flowing rivers, new coastlines would appear as sea levels rose. The sky too would change. A thick carbon-rich atmosphere would influence the colour and clarity of the air. Clouds might be more abundant, driven by increased evaporation from warming oceans. Rainstorms could be intense, fueled by the combination of heat and moisture. This period of warmth would not last forever. As weathering continued to draw carbon dioxide out of the air, the greenhouse effect would weaken. Temperatures would gradually fall. Ice might return to higher latitudes, though not necessarily to the same global extent as before. The planet would settle into a new balance, different from both the deep freeze of snowball Earth and the hothouse conditions of the immediate aftermath. Looking at the Great Thaw through the lens of a unified climate, what stands out is the way the same feedback loops that once drove the planet toward cold now drove it toward warmth. The system did not need an external intervention. It carried within it the mechanisms for both extremes and for the transitions between them. This idea has a certain quiet symmetry to it. The planet, in a sense, contains the instructions for its own change. The sun provides a steady stream of energy. The interior releases gases. The surface processes move those gases between different reservoirs. The balance shifts back and forth over long spans of time. There's also something deeply interconnected about the way different parts of the Earth system participate in this story. The mantle and crust influence the atmosphere through volcanic activity. The atmosphere influences the oceans through heat and gas exchange. The oceans influence the surface through circulation and chemistry. Life, in turn, influences the atmosphere by producing and consuming gases. None of these elements acts in isolation. Each one is part of a loop that feeds back into the others. The Great Thaw makes these connections especially visible. A change that begins deep underground in the release of carbon dioxide from magma eventually leads to changes in the sky, the sea, the land, and the living world. A process that starts as a slow accumulation of invisible gas ends with glaciers melting, rivers flowing, and ecosystems expanding. There is a certain scale-shifting quality to this story that can be hard to keep in mind. On one level, it's about individual molecules of carbon dioxide and water moving between different states and places. On another level, it's about entire continents being reshaped by ice and water, about the chemistry of the oceans changing, about the trajectory of life itself. From the perspective of the planet, these levels are not separate. They're all part of the same system, operating simultaneously across different sizes and timescales. If you let your attention drift for a moment to the present, there's a faint echo of this ancient process in the world around you. The air you breathe contains carbon dioxide that was once locked in rocks or dissolved in oceans. The water you drink has been part of clouds, rivers, and seas. The warmth in your environment comes ultimately from the same sun that guided the ancient Thaw. Of course, the timescales are very different. The changes we notice day to day or year to year are tiny ripples compared to the waves of transformation that define events like Snowball Earth and the Great Thaw. But the underlying principles are the same. Energy flows, gases move, feedback loops operate. Returning to that thawing world, it's worth thinking about the emotional quality of the image, even if no one was there to feel it at the time. A planet emerging from ice carries a sense of release. Water returning to the surface, movement returning to the air, light reaching into the ocean again. It's a transition from stillness to motion, from a world dominated by reflection to one dominated by absorption and exchange. This shift also marks a turning point in the idea of a unified climate. During the frozen phase, unity meant cold everywhere, a kind of planetary sameness enforced by ice. During the warm aftermath, unity meant heat and moisture spreading across the globe, driving high levels of weathering and circulation. In both cases, the defining feature is not local variation, but global coherence. As the planet continued to change, that coherence would begin to break into more complex patterns. Continents would move into new positions, mountain ranges would rise higher, ice would become more confined to the poles, vegetation would spread across the land, creating new ways for sunlight and water to interact with the surface. These developments would introduce more regional character into the climate system. The world would become, over time, a place of distinct zones and patterns rather than a single dominant state. But before that complexity fully took hold, the Great Thaw stands as a reminder of how deeply connected the planet's systems are, and how capable they are of shifting together from one extreme to another. Beneath every ocean basin and every stretch of land, far below the reach of roots, rivers, and even the deepest mines, there is a part of the planet that never truly rests. Rock that looks solid and permanent at the surface is, at depth, warm, mobile, and slowly moving, carrying heat and material upward in a quiet, relentless flow. This hidden movement is what gives rise to volcanoes, shifting plates, and the long, subtle exchange of gases between the Earth's interior and the sky above. When people speak of the planet breathing, this is what they are often pointing toward. The idea that stone itself participates in a slow exhale that shapes the air, the oceans, and over immense spans of time, the climate of the entire world. It's easy to think of volcanoes as rare, dramatic events, moments when a mountain explodes or lava pours across the landscape in fiery rivers. Those moments are certainly part of the story, but they are only the most visible expressions of a much broader and steadier process. Most of the planet's volcanic activity doesn't happen on land at all. It happens along long winding seams in the ocean floor, where tectonic plates pull apart and molten rock rises to fill the gap. There, deep beneath kilometers of water, lava oozes out and cools, creating new crust and releasing gases into the surrounding sea. This constant creation of a new rock is part of the planet's long-term cycle. Old crust is pushed back down into the mantle at subduction zones, where one tectonic plate slides beneath another. As that rock sinks, it carries with it water and carbon that were once part of the surface. Heat and pressure change these materials, and some of the carbon is eventually released again through volcanic activity. In this way, carbon moves in a vast loop between the deep Earth and the atmosphere, a cycle that operates on timescales so long they can be hard to imagine. Carbon is central to this story because of its role in regulating temperature. In the atmosphere, carbon dioxide acts as a greenhouse gas, trapping heat and keeping the surface of the planet warmer than it would otherwise be. Without it, Earth would be a much colder, less hospitable place. With too much of it, the planet can become uncomfortably warm. The balance between carbon being added to the air and carbon being removed is one of the key controls on the climate. Volcanoes are one of the main sources of carbon dioxide in this balance. When magma rises, it carries dissolved gases with it. As the pressure decreases near the surface, those gases come out of solution and are released into the air. Carbon dioxide, water vapour, sulphur compounds and other gases pour out through vents and fissures, sometimes in explosive bursts, sometimes in quiet, invisible streams. On a human timescale, the amount of carbon dioxide released by volcanoes each year is small compared to what modern society emits through burning fossil fuels. But on a geological timescale, that steady volcanic output is one of the dominant sources of atmospheric carbon. Over millions of years, it can build up to levels that significantly alter the planet's temperature. This is where the idea of breathing stone becomes especially fitting. The planet, through its interior processes, slowly exhales carbon into the atmosphere. That carbon doesn't stay there forever. It is gradually drawn back down into the solid Earth through a different set of processes that involve water, rock, and life. One of the most important of these processes is chemical weathering. When rain falls, it absorbs carbon dioxide from the air, forming a weak acid. This slightly acidic water reacts with certain minerals in rocks, especially silicate minerals, breaking them down and releasing elements like calcium and magnesium. The carbon from the carbon dioxide becomes part of dissolved compounds that are carried by rivers to the ocean. In the ocean, these dissolved materials can be used by organisms to build shells and skeletons made of calcium carbonate. When those organisms die, their shells can settle to the seafloor and become part of the sediment. Over time, layers of this sediment are buried, compacted, and turned into rock. Eventually, through the slow movement of tectonic plates, some of this carbon-rich rock is carried back into the mantle, completing the cycle. This entire loop, from volcanic release to chemical weathering to sedimentation to subduction and back to volcanic release again, is known as the long-term carbon cycle. It operates over hundreds of thousands to millions of years. It is one of the main reasons the Earth's climate has remained within a range that allows liquid water to exist on the surface for most of the planet's history. What makes this cycle especially interesting in the context of a unified climate is that it works on a planetary scale. Carbon dioxide released in one region doesn't stay there. It mixes into the global atmosphere. Rain that falls in one place carries carbon that may have come from volcanic gases released somewhere else. Rivers transport that carbon to oceans that are connected across the globe. Sediments form on seafloors far from where the carbon originally entered the system. In a world where the oceans were more continuous and the circulation of air and water more global, this cycle would have been even more tightly linked. The planet's slow exhale of carbon through volcanoes would influence temperatures everywhere, and the planet's slow inhale through weathering and sedimentation would respond to those temperatures in turn. There is a feedback loop here that has a certain quiet elegance. When the planet is warm, rainfall tends to be more intense. More rain means faster chemical weathering. Faster weathering removes carbon dioxide from the atmosphere more quickly, which cools the planet. When the planet is cool, rainfall is often reduced, and large areas may be covered in ice. Weathering slows down. Carbon dioxide released by volcanoes begins to build up in the air, which warms the planet. This feedback doesn't act quickly. It's not something you would notice over a human lifetime. But over millions of years, it provides a kind of thermostat for the planet, helping prevent the climate from drifting too far into either extreme for too long. Volcanoes, in this sense, are not just agents of destruction or creation. They are part of a regulatory system that ties the deep earth to the sky. Their eruptions add carbon to the air, but that addition is balanced over time by the surface processes that remove it. During periods like snowball Earth, this balance is disrupted in a particular way. When the surface is covered in ice, chemical weathering nearly stops. Rivers don't flow. Rain doesn't fall on exposed rock. The planet's ability to draw carbon dioxide out of the atmosphere is greatly reduced. Volcanoes, however, keep releasing it. The slow exhale continues, but the inhale is blocked. This leads to a build-up of greenhouse gases that eventually become strong enough to overcome the cooling effect of the ice. The result is the great thaw we explored earlier. In that moment, the planet's interior and surface processes come back into alignment. Weathering resumes. Carbon begins to be drawn down again. The cycle restarts. Looking at this system from a distance, it can feel almost intentional, as if the planet is actively regulating itself. In reality, it's the outcome of basic physical and chemical processes interacting over long periods of time. There is no plan or goal, just a set of relationships that tend to produce a certain kind of balance. Another important part of this story is the role of tectonic plates in shaping where and how volcanoes operate. The surface of the Earth is divided into large moving plates that float on the softer, warmer mantle beneath. Where these plates pull apart, magma rises and creates new crust, often accompanied by volcanic activity. Where they collide, one plate may be forced down into the mantle, carrying water and carbon-rich sediments with it. The arrangement of these plates has changed dramatically over the planet's history. Continents have come together to form supercontinents and then broken apart again. Ocean basins have opened and closed. These changes influence the length and location of plate boundaries, which in turn affects the amount and distribution of volcanic activity. For example, when a supercontinent breaks apart, it creates long rift zones where new ocean crust forms. This can lead to increased volcanic activity along those rifts, releasing more carbon dioxide into the atmosphere. When continents collide and mountain ranges form, large areas of fresh rock are exposed to the air and rain, increasing the rate of chemical weathering and drawing more carbon out of the atmosphere. In this way, the movement of continents and the breathing of stone are linked. The shape of the planet's surface influences how much carbon is added to the air and how much is removed. The climate responds to those changes. The climate in turn influences how fast weathering happens and how much sediment is carried to the ocean. The loop continues. It's also worth thinking about the role of the oceans in this cycle. When carbon dioxide dissolves in seawater, it changes the chemistry of the ocean, making it more acidic. This can affect the ability of organisms to build shells and skeletons from calcium carbonate. Over long periods, changes in ocean chemistry can influence how much carbon is locked away in sediments. In a more unified ocean system, these chemical changes would spread widely. A shift in the balance of carbon in one region could influence conditions across large portions of the global sea. This adds another layer of planetary scale connection to the breathing stone concept. Volcanic activity also releases other substances that can affect climate, at least temporarily. Sulfur dioxide, for example, can form tiny particles in the atmosphere that reflect sunlight back into space. Large volcanic eruptions can lead to short-term cooling by increasing the amount of these reflective particles. On a geological timescale, this effect is usually brief compared to the long-term warming influence of carbon dioxide, but it can still leave a mark in the climate record. In the deep past, periods of intense volcanic activity, such as those associated with massive lava flows called large igneous provinces, may have had dramatic effects on the climate. These events can release enormous amounts of gases over relatively short periods of geological time. Some are linked to mass extinctions and major shifts in the planet's environment. Even in these more dramatic moments, the same basic processes are at work. Carbon is released, the climate warms, weathering and sedimentation eventually respond, drawing carbon back down. The system finds a new balance. There is a certain slowness to all of this that can be hard to reconcile with the suddenness we often associate with volcanoes. We tend to focus on the eruption, the explosion, the lava. But the more important story in terms of climate is the quiet, continuous release of gases that happens day after day, year after year, along thousands of kilometers of plate boundaries. This steady exhale of the planet's interior is one of the reasons the idea of a unified climate makes sense in the deep past, when the main source of greenhouse gases is spread across a global network of volcanic systems, and when the main sink for those gases operates through global processes like weathering and ocean circulation, the climate naturally takes on a planetary character. It's also a reminder of how deeply time is woven into this story. None of these processes care about decades or centuries. They operate on scales that dwarf human history: a mountain range rising, an ocean basin opening, a supercontinent breaking apart. These are the events that shape the long-term flow of carbon between rock and sky. Thinking about this can bring a certain quiet perspective. The ground beneath you, which feels so solid and unchanging, is part of a system that is, in its own slow way, alive with motion. The air around you, which feels so immediate and fleeting, is connected to processes that began deep in the planet's interior and will continue long after any one moment has passed. The concept of breathing stone also ties back to the idea of a unified Earth in another way. It highlights how the solid, liquid, and gaseous parts of the planet are not separate realms, but parts of a single system. Rock becomes gas. Gas becomes dissolved in water. Water carries it back to rock. The boundaries between these states are more fluid than they appear at first glance. This fluidity is part of what allowed the planet to move through such different climate states in its history. A frozen world can become a warm one. A warm one can cool again. The deep Earth and the surface Earth are in constant conversation, even if that conversation unfolds over spans of time that are almost beyond comprehension. High above the restless surface of oceans and the slow breathing movement of stone, there was another layer of the planet quietly learning how to behave. It wasn't solid or liquid. It couldn't be held or carved. It shifted shape from moment to moment, responding to heat, moisture, and motion in ways that were both simple and endlessly complex. This was the sky of the young Earth, and in its early forms it played a role that went far beyond making weather. It helped decide how much energy the planet kept, how much it lost, and how tightly the climate of distant regions would be linked together. To think about clouds in the deep past, it helps to forget for a moment the tidy categories we use today. We talk about cumulus, stratus, cirrus, storm fronts, jet streams, and pressure systems, as if the sky were a well-organized machine with clearly labelled parts. On a young Earth, the atmosphere was still experimenting. The mix of gases was different. The distribution of land and sea was unfamiliar. The temperature contrasts that drive modern wind patterns were softer or arranged in other ways. The sky above that world was not following the same script we see now. What it did have, from the very beginning, was water. Water vapour is a powerful player in any atmosphere. It is light, mobile, and full of energy. When it condenses into liquid droplets or ice crystals, it releases heat into the surrounding air. When it evaporates, it absorbs heat. This simple change of state, from vapour to liquid to ice and back again, is one of the main engines behind atmospheric motion. On the early Earth, with vast open oceans and high levels of greenhouse gases keeping temperatures relatively warm, evaporation would have been widespread. Water would rise into the air in invisible streams, carried upward by warm, buoyant currents. As that air rose and cooled, the water vapour would condense, forming clouds. These clouds were not just decorations in the sky. They were active participants in the planet's energy balance. Clouds interact with sunlight and heat in two important ways. On the one hand, they reflect incoming sunlight back into space, which has a cooling effect. On the other hand, they trap some of the heat that the planet radiates upward, which has a warming effect. The overall impact depends on the type, height, and thickness of the clouds. Low, thick clouds tend to reflect a lot of sunlight and cool the surface. High, thin clouds are better at trapping heat and tend to warm the planet. The balance between these different kinds of clouds can tilt the climate in one direction or the other. In a young atmosphere where the composition of the air and the amount of moisture were different, the mix of cloud types may have been different as well. Some scientists suggest that higher levels of greenhouse gases and a warmer surface could have favoured the formation of high-altitude clouds. If so, the sky itself would have contributed to keeping the planet warm by trapping heat, reinforcing the effect of the gases in the atmosphere. At the same time, the wide open oceans would have provided an almost endless source of moisture. This could lead to extensive cloud cover, spreading across large portions of the planet rather than forming in isolated systems. A sky that is often cloudy over much of the globe would further smooth out temperature differences. Sunlight would be diffused rather than striking the surface in sharp, localized beams. Daytime heating would be gentler. Nighttime cooling would be moderated by the insulating effect of cloud layers. This kind of sky supports the idea of a more unified climate. When clouds and moisture are distributed broadly, they help link the energy balance of one region to that of another. A change in temperature in one area can influence evaporation, cloud formation, and rainfall elsewhere, creating connections that stretch across continents and oceans. Wind is the other major actor in this atmospheric story. Wind is simply air in motion, driven by differences in pressure that arise from differences in temperature. Warm air expands and becomes less dense, creating areas of lower pressure. Cool air is denser and sinks, creating areas of higher pressure. Air moves from high pressure to low pressure, and the rotation of the planet bends those movements into large-scale patterns. On a modern Earth, these patterns are strongly shaped by the contrast between warm tropics and cold poles, and by the presence of major landforms. In the ancient world, those contrasts and barriers were often less pronounced. The result may have been broader, more continuous wind systems that wrapped around the globe in wide loops. These winds did more than move air. They pushed on the surface of the oceans, helping drive currents. They carried moisture from the sea over land, where it could fall as rain, and begin the process of chemical weathering. They transported dust and tiny particles that could serve as seeds for cloud formation, influencing where and how clouds developed. The atmosphere and the ocean, in this way, were tightly coupled. Changes in one affected the other. A warmer ocean led to more evaporation, which led to more clouds, which influenced how much sunlight reached the surface. Stronger winds altered ocean circulation, which changed how heat was distributed, which fed back into atmospheric motion. This loop of interactions creates what scientists call a coupled system, where no single part can be fully understood in isolation. In a world with fewer regional distinctions, this coupling would tend to operate on a more global scale. The sky above one ocean basin would be influenced by conditions in another. The rainfall on a stretch of land could depend on evaporation from water thousands of kilometers away. One way to see evidence of this ancient global behavior is through the chemical signatures left behind in rocks. Certain minerals form only under specific atmospheric conditions. For example, the presence or absence of oxygen in the air influences how iron and other metals are deposited. Layers of sediment that show similar chemical characteristics across wide areas suggest that the atmosphere above them shared common properties. There are also clues in the isotopes of elements like sulfur. Some ancient rocks show patterns that indicate the atmosphere once allowed certain wavelengths of sunlight to reach the surface, something that would only happen if there was little or no ozone layer. This tells us not just about the composition of the air, but about how sunlight interacted with it, which in turn influences cloud formation and climate. Rainfall is another key piece of the puzzle. In a unified climate system, precipitation patterns would be less tied to fixed geographic features and more to broad atmospheric circulation. Instead of monsoons driven by the contrast between land and sea temperatures, or rain shadows created by mountain ranges, the young Earth may have experienced more evenly distributed rainfall over large areas. This doesn't mean it rained the same amount everywhere. There would still be variations based on latitude, prevailing winds and ocean temperatures, but the overall pattern might have been smoother, with fewer sharp boundaries between wet and dry regions. This has implications for how the surface of the planet evolved. Rainfall drives erosion and weathering. When water flows over rock, it breaks it down, carrying minerals and sediments into rivers and oceans. Over time, this reshapes landscapes and influences the chemistry of the sea and the air. If rainfall was more globally distributed, then weathering would also be more globally distributed. This would strengthen the idea of a planetary-scale carbon cycle, where carbon dioxide released by volcanoes is drawn down by chemical reactions happening across much of the surface, rather than being concentrated in specific regions. Clouds and rainfall also affect how much sunlight reaches the surface, not just through reflection, but through absorption and scattering. A sky filled with clouds creates a softer, more diffused light. This can influence surface temperatures and the way energy is absorbed by land and water. In a young world without forests, grasses, or large land plants, the surface would have been mostly rock and water. Both of these surfaces respond differently to sunlight than vegetation does. Bare rock can heat up quickly, but it also cools down quickly. Water changes temperature more slowly. The presence of widespread cloud cover would help moderate these differences, preventing extreme heating during the day and extreme cooling at night. Day and night themselves would have felt different in that environment. With shorter days in the early Earth's history, as the planet rotated faster, the cycle of heating and cooling would have been more rapid. Clouds, by insulating the surface, would help smooth out those rapid changes, contributing to a more even temperature profile over the course of each rotation. The sky also played a role in protecting the surface. As oxygen accumulated in the atmosphere, it allowed the formation of ozone in the upper layers. Ozone absorbs much of the sun's harmful ultraviolet radiation. This shield made it safer for life to exist close to the surface and eventually on land. But before the ozone layer was well established, the atmosphere was more transparent to high-energy sunlight. This could influence not just life, but also the chemistry of the air itself. Ultraviolet radiation can break apart molecules, creating reactive fragments that go on to form new compounds. This kind of chemistry can affect the abundance of greenhouse gases and aerosols, which in turn influence cloud formation and climate. Aerosols, tiny particles suspended in the air, are especially important for clouds. Water vapour needs something to condense around. Dust, salt, and chemical particles provide those surfaces. Volcanic eruptions are a major source of aerosols, injecting fine ash and sulfur compounds into the atmosphere. In the young Earth, with active volcanism, the sky may have often been seeded with these particles, promoting cloud formation over wide areas. This adds another layer to the connection between the planet's interior and its climate. The breathing of stone through volcanic activity not only released greenhouse gases, but also supplied the sky with the raw materials needed to build clouds. Those clouds, in turn, influenced how much of the sun's energy stayed with the planet, and how much was reflected away. It's a web of interactions that stretches from deep below the surface to the highest reaches of the atmosphere. Heat from the mantle influences volcanic output. Volcanic output influences atmospheric composition. Atmospheric composition influences cloud formation. Clouds influence temperature. Temperature influences weathering. Weathering influences the carbon cycle. The loop closes back on the interior. In a more fragmented modern climate system, these loops still exist, but their effects can be more localized. A volcanic eruption might influence regional weather. A shift in ocean temperature might affect specific climate zones. In the ancient world, with fewer barriers and smoother gradients, these loops would have been more likely to play out on a global stage. Thinking about the sky in this way can change how it feels to look up at it. Even now, the clouds you see drifting overhead are part of a system that links your location to distant oceans and faraway sources of heat. The moisture in those clouds may have evaporated from a sea on the other side of the planet. The tiny particles that help those droplets form could have come from desert dust or the spray of waves. On the young Earth, that sense of connection would have been even more pronounced. The sky would have been a truly planetary layer, tying together the surface and the deep earth, the sun and the sea, in a continuous exchange of energy and matter. There is also a temporal dimension to this story. Clouds form and dissipate in hours or days. Winds shift over seasons. Atmospheric composition changes over thousands or millions of years. The sky operates on multiple timescales at once, from the fleeting to the enduring. In a unified climate, these timescales are woven together, with short-term processes riding on top of long-term trends. For example, A single storm is a local, temporary event, but the pattern of where storms tend to form and how often they occur is shaped by the global circulation of the atmosphere and the distribution of heat across the planet. On the young Earth, that global circulation would have been influenced by the broader, more uniform energy balance we've been discussing. This means that even small-scale features of the weather were, in a sense, echoes of planetary-scale processes. A cloud forming over one patch of ocean was connected, through the movement of air and water, to conditions far beyond the horizon. As the planet continued to evolve, the sky's role would become more complex. The rise of land plants would change how much water was returned to the air through transpiration. The growth of ice caps would alter how sunlight was reflected. The build-up of oxygen and the strengthening of the ozone layer would change the way the upper atmosphere interacted with solar radiation. All of these developments would introduce new layers of variation into the climate system. Regional patterns would become more pronounced. Seasons would become more familiar. The unified global character of the early atmosphere would give way to a more textured, locally differentiated sky. But before that shift took full hold, the clouds over the young world were part of a simpler, broader system. They helped distribute energy, smooth out extremes, and link distant regions through shared patterns of motion and moisture. There's a certain quiet beauty in that idea, even if the world itself was anything but gentle. The sky acting as a kind of connective tissue, binding the planet's surface into a single breathing whole. Before forests cast shadows across the land or animals left tracks in soft soil, the planet was already home to life that had learned how to exist within a world shaped by broad, sweeping forces rather than sharply divided environments. In this earlier phase of Earth's story, organisms didn't move between deserts and rainforests, or adapt to icy poles and warm tropics as separate challenges. Instead, they lived within a climate system that, for long stretches of time, behaved as a single, connected whole. Understanding how those early forms of life adapted to such a world means looking not at dramatic survival stories, but at quiet, persistent adjustments that unfolded over immense spans of time. The earliest known life on Earth was simple in structure but remarkably resilient in behaviour. Microorganisms, likely similar to modern bacteria and archaea, appeared in the oceans more than 3.5 billion years ago. These tiny beings did not rely on complex organs or specialised tissues. Their entire existence played out at the level of chemistry. They absorbed substances from the water around them, transformed those substances through metabolic reactions, and released new compounds back into their surroundings. In a unified climate, this chemical relationship between life and environment took on a planetary character. The water these organisms lived in was not confined to small, isolated basins. It was part of a global ocean system that mixed, circulated, and shared its properties across vast distances. Temperature, salinity, and chemical composition were shaped by large-scale processes rather than local quirks. This meant that the conditions an organism experienced in one region were, in many respects, similar to those experienced far away. That similarity did not mean sameness in every detail, but it did create a kind of baseline. Early life did not have to navigate a world of sharply contrasting habitats. Instead, it faced gradients, slow changes from one set of conditions to another, spread across thousands of kilometres and millions of years. Adaptation, in this context, was less about quick responses to sudden environmental shifts and more about long-term tuning to a relatively stable global backdrop. Energy is the first requirement for any form of life, and in the ancient oceans, energy came from two main sources. One was chemical, and the other was light. Chemical energy was available in places where water interacted with the planet's interior, such as around hydrothermal vents on the seafloor. There, hot, mineral-rich fluids rose from below, creating environments where certain chemical reactions could release energy that organisms could use. These deep-sea habitats were not influenced directly by sunlight, but they were still part of the unified system. The chemistry of the ocean above affected the composition of the fluids below. The circulation of water carried dissolved substances from the surface down to the depths and back again. Even in these dark environments, the global movement of the ocean played a role in shaping the conditions for life. The second source of energy, sunlight, became increasingly important as life evolved the ability to capture it. Photosynthesis, the process by which organisms use light to convert carbon dioxide and water into organic compounds and oxygen, is one of the most significant innovations in the history of life. It changed not only how organisms obtained energy, but also the composition of the atmosphere and the chemistry of the oceans. In a world with fewer barriers and more even distribution of sunlight and warmth, photosynthetic organisms could spread widely. Shallow seas and broad continental shelves provided extensive sunlit environments where these early life forms could thrive. The global circulation of the oceans helped distribute nutrients and trace elements that supported their growth. The unified nature of the climate system meant that the success of photosynthesis in one region could influence conditions across the planet. As photosynthetic organisms released oxygen into the water and the air, they began to transform the environment in a fundamental way. Oxygen is a highly reactive gas. In the oceans, it combined with dissolved iron and other elements, forming solid compounds that settled to the seafloor. In the atmosphere, it eventually built up to levels that allowed the formation of an ozone layer, which altered how sunlight interacted with the planet. This process, often called the Great Oxidation Event, did not happen overnight. It unfolded over hundreds of millions of years. During that time, life and climate were deeply intertwined. The global spread of oxygen-producing organisms meant that changes in the composition of the air and water were not confined to a single region. They were planetary in scope. For organisms that did not use oxygen, this shift was a challenge. Many early life forms were adapted to environments without free oxygen, and the rise of this gas created conditions that were, for them, toxic. Some retreated to niches where oxygen levels remained low, such as deep sediments or isolated pockets of water. Others disappeared. At the same time, new forms of life evolved that could take advantage of oxygen's chemical potential, leading to more efficient ways of extracting energy from organic compounds. In a unified climate, these biological changes rippled outward. The rise of oxygen influenced the abundance of other gases, such as methane, which is a powerful greenhouse gas. As oxygen levels increased, methane was broken down more quickly. This reduced the atmosphere's ability to trap heat and may have contributed to global cooling events, including the glaciations we explored earlier. Here, life is not just adapting to climate, it is helping shape it. The actions of countless microscopic organisms spread across a connected ocean and atmosphere alter the planet's energy balance. The unified nature of the system means that these changes do not stay local. They become part of the global climate story. Another aspect of adaptation in a single climate world is the way early organisms dealt with temperature. In a planet without sharp seasonal contrasts or extreme regional differences, temperature changes were often gradual. This favoured organisms that could tolerate a range of conditions rather than those specialised for a narrow niche. Many modern microorganisms are what scientists call extremophiles, capable of surviving in very hot, very cold, very salty, or very acidic environments. It's possible that early life was similarly flexible, not because it needed to survive in extreme places, but because the global system could still swing between warmer and cooler states over long periods of time. A slow cooling trend or a gradual warming would give organisms time to adjust their biochemistry. Enzymes, the proteins that drive metabolic reactions, are sensitive to temperature. Small changes in their structure can shift the range of conditions under which they work effectively. Over many generations, population can evolve enzymes better suited to the prevailing climate. In a unified system where changes happen broadly and slowly, this kind of adaptation can occur on a planetary scale. Salinity, the concentration of dissolved salts in the water, is another factor that early life had to navigate. The chemistry of the ancient oceans was not identical to what we see today. Volcanic activity, weathering of rocks, and the circulation of water all influence the mix of ions and minerals in the sea. In a connected ocean, changes in salinity in one region could be spread through currents to others. This meant that organisms were often dealing with a relatively consistent chemical environment across large areas. Adaptations that worked in one place were likely to work in many others, which could help explain how certain forms of life became widespread. Movement, even at the microscopic scale, also took on a different character in this world. Early organisms did not migrate in the way animals do, but they could be transported by water. Currents could carry them across vast distances, introducing them to new regions with similar conditions. This kind of dispersal, combined with a unified climate, would promote the spread of successful adaptations and reduce the degree of isolation between populations. Over time, as the planet developed more geographic complexity, this would change. Continents would break apart. Basins would become more isolated. Mountain ranges would rise, altering winds and rainfall. Climate zones would become more distinct. But in the earlier, more unified phase, the ocean acted as a kind of global highway for life. There is also the matter of timing. In a world without strong seasons, the cycles that organisms responded to were not annual. They were often tied to other rhythms, such as changes in ocean chemistry, long-term shifts in temperature, or the slow movement of nutrients through the water. Some modern microorganisms still show traces of these kinds of rhythms. They respond to cycles of light and dark, but also to changes in nutrient availability and chemical gradients that can operate over longer timescales. These responses hint at an ancient heritage, one shaped in a world where the dominant patterns were planetary rather than local. As life became more complex, it began to create new kinds of interactions with the climate system. The development of larger multicellular organisms changed how matter and energy moved through ecosystems. Organic material produced at the surface could sink to the depths, carrying carbon and nutrients with it. This biological pump, as scientists call it, is an important part of how the oceans store carbon today. In a unified ocean system, this pump would operate on a global scale. The growth of life in sunlit waters near the surface would influence the chemistry of deep waters far away, as organic particles drifted down and were broken down by microbes. This adds another layer to the connection between life and climate, one that links biological activity at the surface to conditions in the deep sea and, through sedimentation, to the long-term carbon cycle. The appearance of more complex life also introduced new demands. Larger organisms require more energy and more stable conditions. The aftermath of global glaciations with warm temperatures, abundant nutrients, and widespread shallow seas may have created an environment that supported this increase in complexity. From this perspective, the unified climate of the early Earth is not just a backdrop. It is part of the story of how life became what it is. A connected global system allowed certain innovations to spread widely. It also meant that major changes, like the rise of oxygen, had far-reaching consequences. There is an interesting contrast here with the world we live in now. Today, life is adapted to a patchwork of climates. Species specialize in particular regions, temperatures, and conditions. A plant that thrives in a tropical rainforest may not survive in a desert or a polar environment. This specialization is, in part, a response to the increased complexity and variability of the planet's climate system. In the ancient world, with fewer sharp boundaries, the pressures were different. Adaptation favoured flexibility and broad tolerance. Life was, in a sense, learning to live with the planet as a whole, rather than with a specific place on it. It's also worth considering the scale of time involved. The changes we're talking about unfolded over hundreds of millions of years. Entire lineages of organisms rose, adapted, and disappeared in the span of what, to the planet, might be considered a single long chapter. During that time, the climate system itself was not static. It moved between warmer and cooler states. It responded to changes in the sun, in volcanic activity, in the arrangement of continents, and in the composition of the atmosphere. Life had to navigate all of these shifts, sometimes as a passenger, sometimes as a driver. This dynamic relationship is one of the defining features of Earth's history. The planet is not just a stage on which life plays out its story. Life and the planet co-author that story, each influencing the other in ways that are sometimes subtle and sometimes profound. Thinking about early organisms in a unified climate can also bring a sense of scale to our own place in the world. The air you breathe contains oxygen produced by ancient photosynthetic life. The carbon in your body was once part of the atmosphere, the ocean, or the rock. The water in your cells has been moving through this planet's systems for billions of years. In that sense, you are connected physically to this deep past. The conditions that shaped the earliest life also helped shape the world you inhabit now. The unified climate of the ancient Earth set the stage for the diversity of environments and organisms that would follow. As the planet continued to change, the climate system would become more textured and more regional. Ice would become more confined to the poles. Forests and deserts would emerge. Mountain ranges would carve the atmosphere into complex patterns of wind and rain. Life would respond by diversifying, specializing, and filling every available niche. But before that rich patchwork took shape, there was a long period when the dominant forces were global, when the atmosphere and oceans acted as planetary connectors, and when life adapted not to a specific place, but to the Earth as a whole. Across a span of time so long it barely fits inside human language, the surface of the planet began to change its posture. What once felt like a broad, connected face of water and low-lying land slowly rose, folded, and separated into distinct pieces. The unified world we've been exploring did not vanish in a single dramatic moment. Instead, it gradually gained edges, barriers, and contours that encouraged the climate to behave less like a single, planetary rhythm and more like a collection of regional patterns. This shift, driven by the steady movement of continents and the slow rise of mountains, marks the beginning of a more familiar Earth, one where here and there started to mean different things in the air above and the weather below. The engine behind this transformation lies deep beneath the surface in the restless motion of tectonic plates. These enormous slabs of crust float on the warmer, softer mantle below, moving at a pace that is almost impossible to notice in a lifetime, but impossible to ignore over millions of years. They drift apart, collide, slide past one another, and sometimes plunge back into the planet's interior. Every one of these motions reshapes the geography of the surface, and in doing so, it reshapes the pathways along which air and water move. Early in Earth's history, land masses were often clustered together or arranged in ways that left large, open stretches of ocean. Over time, these clusters broke apart and reassembled into new configurations. Supercontinents formed and then fractured. Oceans opened where land once stood, and seas closed where water once flowed freely. Each rearrangement changed the way sunlight, wind, and currents interacted with the surface. When continents drift closer to the poles, ice becomes more likely to form on land. Ice on land reflects sunlight and encourages cooling, reinforcing the development of colder regions. When large land masses sit near the equator, they tend to absorb more heat and drive strong evaporation and rainfall, creating warm, wet climates. The position of continents, in other words, acts like a set of dials on the planet's climate system, adjusting where heat is absorbed, where it is reflected, and where moisture is carried. One of the most significant changes that comes with moving continents is the creation of barriers. Open ocean allows currents to flow in long looping paths, spreading heat and chemical properties across the globe. A rising land mass can interrupt those paths. A narrow seaway can focus currents into faster, more concentrated flows. A wide continent can block a current entirely, forcing water to take a different route. These changes in ocean circulation have far-reaching effects. A current that once carried warm water toward a particular region might be diverted, leaving that area cooler and drier. Another region might suddenly receive more heat and moisture than it did before. Over time, these shifts help carve the planet into zones with distinct climatic personalities. Mountains add another layer of complexity. When tectonic plates collide, the crust can crumple and rise, forming long chains of peaks. These high places are not just features of the landscape, they are active participants in the climate system. Air moving across the surface is forced upward when it encounters a mountain range. As it rises, it cools, and the moisture it carries can condense and fall as rain or snow. On the windward side of a mountain, this can lead to lush, wet conditions. On the leeward side, the air descends, warms and dries, creating what is known as a rain shadow, an area that receives much less precipitation. Before large mountain ranges existed, air could move more freely across the surface, and rainfall patterns were often broader and more evenly distributed. As mountains rose, they introduced sharp contrasts over relatively short distances. A green, wet region could exist just a few hundred kilometers away from a dry, arid one, all because of the way a wall of rock redirected the flow of air. These geographic features didn't just create regional differences, they also influenced the long-term balance of carbon in the atmosphere. Mountain building exposes fresh rock to the surface. Rain falling on this rock drives chemical weathering, which draws carbon dioxide out of the air and locks it into minerals that eventually reach the ocean. Large, newly formed mountain ranges can significantly increase the rate of this process, contributing to global cooling over geological timescales. In this way, the breaking apart of continents and the rising of mountains fed back into the climate system at both regional and planetary levels. Local changes in weather patterns were linked to global changes in atmospheric composition. Another important development in this story is the formation of distinct ocean basins. As continents moved, they created enclosed or semi-enclosed seas. These bodies of water could develop their own circulation patterns, somewhat isolated from the global ocean. Temperature, salinity, and nutrient levels in these basins could diverge from the rest of the world, creating unique marine environments. This isolation encouraged the development of regional differences in life as well. Species in one basin might evolve in relative separation from those in another, leading to greater biological diversity. Climate and life began to co-evolve in more localized ways, with specific adaptations tied to particular regions. The atmosphere responded to these changes too. The distribution of land and sea affects how quickly the surface heats up and cools down. Land tends to warm and cool more rapidly than water. Large continents can develop strong temperature contrasts between their interiors and their coastlines. This drives seasonal wind patterns, such as monsoons, where air flows in one direction during part of the year and reverses during another. These seasonal systems represent a major step away from the idea of a single, unified climate. They introduce rhythms that are tied to specific places and specific times of year. Rainfall becomes something that can be expected in certain months and absent in others. Temperature swings become more pronounced in some regions than in others. The tilt of the Earth's axis, which has always influenced how sunlight is distributed across the planet over the course of a year, becomes more visible in the climate system as these geographic features develop. With ice caps at the poles and large continents at various latitudes, the contrast between summer and winter grows stronger. The planet's climate starts to express its annual cycle in more dramatic ways. Ocean gateways play a particularly interesting role in this transition. These are narrow connections between larger bodies of water, formed when continents move close together or pull apart. A change in the width or depth of one of these gateways can alter global circulation patterns. For example, when a seaway closes, currents that once flowed through it must find another path. This can change the distribution of heat between the equator and the poles. It can also affect how salty or fresh different parts of the ocean become. which influences where deep water forms and how it moves. These shifts can trigger broader climate changes. A region that begins to receive more warm water may become more temperate. Another that loses that heat supply may cool and develop ice. In this way, a relatively small change in geography can have planetary consequences. As regional climates took shape, the planet became a place of contrasts. Deserts formed in areas where descending air suppressed rainfall. Rainforests developed in regions where warm, moist air rose and released its water. Grassland spread in zones with moderate rainfall and strong seasonal variation. Polar regions became more consistently cold, supporting ice sheets that waxed and waned with changes in the planet's orbit and atmospheric composition. These environments are familiar to us now, but they are the result of a long process of differentiation. They emerge from a world that once behaved more like a single connected system, where large-scale processes smoothed out many of the differences we take for granted. Life responded to this growing complexity by diversifying. Species began to specialize in particular climates and habitats. Plants adapted to dry conditions, developed ways to conserve water. Others thrived in wet, shaded environments. Animals evolved behaviors and body forms suited to specific regions and seasonal cycles. This specialization created feedbacks of its own. Vegetation affects how much sunlight the surface absorbs or reflects. Forests tend to absorb more heat and release more moisture into the air than bare ground or grasslands. This can influence local and even regional climate. The spread of certain types of plants can, over time, reinforce the conditions that favor their own growth. In this way, the breaking apart of the unified climate is not just a physical process driven by rocks and water. It is also a biological one, shaped by the living world that responds to and modifies its surroundings. There is a certain layered quality to this transition. On the deepest level, the movement of tectonic plates rearranges the surface of the planet. On the next level, that rearrangement alters the flow of air and water. On another level, those changes influence where life can thrive. And on yet another, life itself feeds back into the climate system through its effects on the atmosphere and the land. All of these layers interact, creating a world that becomes increasingly textured over time. The smooth gradients of the early Earth give way to sharper boundaries. The broad planetary rhythms are overlaid with local patterns and seasonal cycles. Even so, the global system never disappears entirely. The atmosphere still mixes around the planet. The oceans are still connected by deep currents. Changes in one region can still influence conditions far away. The difference is that these global connections now operate through a more complex network of regional pathways. You can see this today in phenomena like El Niño, where a shift in ocean temperatures in the Pacific Ocean can affect weather patterns across much of the world, or in the way melting ice in polar regions can influence sea levels and ocean circulation globally. These are echoes of the unified system we've been tracing, still present within a more fragmented climate. Thinking about this breaking apart can bring a different perspective on the landscapes we know. A desert is not just a dry place. It is the outcome of large-scale atmospheric circulation patterns shaped by the position of continents and the presence of mountain ranges. A rainforest is not just a wet place. It is part of a global exchange of heat and moisture that traces back to the way sunlight is distributed across the planet. The ground beneath your feet is also part of this story. The rocks you walk on may have formed in an ancient ocean, been buried, uplifted, and exposed again through the movement of plates. The air above you carries moisture that may have evaporated from a distant sea. The climate you experience is the product of a system that links deep time to the present moment. Scattered across the surface of the planet and buried deep beneath it, there are places where time has been quietly folded into matter. These are not archives in any human sense. They have no shelves or labels, no dates written in ink. Instead, they hold their memories in layers, in chemical ratios, in tiny structures that form slowly and remain long after the conditions that created them have passed. When we talk about the memory of a global world, this is what we mean. the Earth has kept a record of its own climate story, written into ice, stone, and the sediments that settle on the ocean floor. One of the most direct ways we read that story is through ice. In the coldest parts of the planet, snowfall does not always melt in the summer. It accumulates year after year, compressing into layers that eventually become ice. Each layer traps a small sample of the air that was present when the snow first fell. Tiny bubbles are sealed inside, preserving a snapshot of the atmosphere from that moment in time. Drill down through an ice sheet in Greenland or Antarctica, and you are, in a sense, moving backward through history. The deeper you go, the older the ice becomes. By analysing the gases in those trapped bubbles, scientists can measure past concentrations of carbon dioxide, methane, and other components of the atmosphere. They can also study the chemistry of the ice itself, which reflects temperature and precipitation patterns at the time it formed. These ice records extend back hundreds of thousands of years, and in some places more than 1 million. They provide a remarkably detailed view of how the climate has changed over that period, showing cycles of warming and cooling, shifts in greenhouse gas levels, and connections between different parts of the Earth system. What makes this especially relevant to the idea of a unified climate is the way these records line up across vast distances. Ice cores taken from opposite sides of the planet often show similar patterns of change, even if the timing and intensity differ slightly. This suggests that many of the major shifts in climate were not purely local events. They were part of a global system responding to changes in energy, atmosphere, and circulation. Ice, however, can only take us back so far. For the deeper past, we turn to rock. The solid Earth holds memories that stretch back billions of years, preserved in layers that were once sediments at the bottom of seas, in crystals that formed from molten magma, and in minerals that grew under specific chemical conditions. Sedimentary rocks are particularly valuable in this regard. They form when particles of sand, mud, and biological material settle out of water and accumulate in layers. Over time, these layers are buried, compressed, and cemented together. Each layer represents a slice of the environment at the time it was deposited. By examining the composition of these layers, scientists can infer things about past climates. The size and shape of the grains can indicate whether the environment was calm or energetic, shallow or deep. The presence of certain minerals can point to warm or cold conditions, to fresh or salty water, to oxygen-rich or oxygen-poor environments. One striking example of this kind of record comes from glacial deposits. When ice moves across the land, it grinds up rock and carries the fragments along. When the ice melts, it leaves behind a distinctive mix of sediments, often poorly sorted, with a wide range of grain sizes. These deposits, called tillites when they turn to rock, are found in places that were once near the equator, indicating that ice once reached far into what are now warm regions. These rocks do not tell us what the temperature was on a particular day, or even in a particular year. What they do tell us is that, over a long period, conditions were cold enough for glaciers to exist in those places. When similar deposits appear on multiple continents, dating to the same general time, it points to a climate event that was global in scale. Another powerful set of clues comes from the chemistry of rocks, especially the ratios of different forms, or isotopes, of certain elements. Isotopes are atoms of the same element that have different numbers of neutrons, and they behave almost identically in chemical reactions, but not quite. Those small differences can be used as traces of environmental conditions. Carbon isotopes, for example, can tell us about the balance between biological activity and inorganic processes. Living organisms tend to prefer one form of carbon over another when they build their tissues. When large amounts of organic material are buried in sediments, it can leave a distinctive signature in the surrounding rocks. Shifts in these signatures over time can indicate changes in the global carbon cycle, which is closely tied to climate. Oxygen isotopes are another key tool. The ratio of different oxygen isotopes in minerals like calcite can reveal information about the temperature of the water in which the mineral formed. Warmer and cooler conditions leave different isotopic fingerprints. By measuring these ratios in rocks from different times and places, scientists can reconstruct patterns of ocean temperature and ice volume over long spans of time. What makes this especially compelling in the context of a unified climate is the consistency of some of these signals across wide areas. When isotopic shifts appear in marine sediments from many parts of the world at roughly the same time, it suggests that the oceans were responding as a connected system to a global change in temperature or chemistry. The ocean floor itself is one of the most extensive and continuous records of the planet's past. Over millions of years, tiny particles of dust, the remains of microscopic organisms and chemical precipitates settle out of the water and form layers of sediment on the seafloor. These layers accumulate slowly, sometimes just a few millimeters per 1,000 years, but over geological time they build up into thick sequences that can be drilled and studied. One of the most important contributors to these sediments is life. Microscopic organisms like foraminifera and coccolithophores build shells out of calcium carbonate. When they die, their shells sink and become part of the sediment. The chemistry of those shells reflects the temperature and composition of the water in which they formed. By analysing them, scientists can reconstruct past ocean conditions with surprising detail. These records show patterns that extend across entire ocean basins. Changes in temperature, nutrient levels, and circulation often appear in sediments from widely separated locations. This points to shifts in the global ocean system, not just local variations. There are also chemical markers in ocean sediments that record changes in the amount of oxygen in the deep sea. In some periods, large areas of the ocean floor appear to have been low in oxygen, which affects the kinds of minerals that form and the way organic material is preserved. These so-called ocean anoxic events are thought to be linked to global climate conditions, such as very warm temperatures and high levels of carbon dioxide. Once again, the key idea is connection. The deep ocean is not a set of isolated basins. It is linked by slow-moving currents that circulate water around the planet over hundreds or thousands of years. A change in temperature or chemistry in one part of this system can eventually be felt elsewhere. The sediments on the seafloor record these changes as part of a global story. Beyond sediments and isotopes, there are also structural features in rocks that serve as climate markers. Certain types of soil, known as paleosols, form under specific environmental conditions. Their chemical composition and physical structure can indicate whether the climate at the time was warm or cool, wet or dry. Similarly, evaporate deposits, which form when water evaporates and leaves behind dissolved salts and minerals, point to arid conditions. Finding these deposits in the geological record can tell us about periods when parts of the planet were dry and hot. When such deposits appear over wide areas, they can suggest broader climate patterns rather than isolated droughts. There are even clues in the way rocks themselves are shaped. Wind can sculpt surfaces in distinctive ways, leaving behind features like sand dunes and abrasion marks. Water can carve channels and leave ripple patterns. Ice can scratch and polish rock. Each of these processes leaves behind a physical memory of the environment in which it occurred. Taken together, these different lines of evidence allow scientists to piece together a picture of Earth's past that goes far beyond any single location. They reveal a planet that has, at times, moved in coordinated ways, with changes in atmosphere, ocean and surface happening across the globe. Reading this record is not a simple task. Rocks can be altered by heat and pressure. Layers can be folded, faulted or eroded away. Chemical signatures can be overprinted by later processes. Interpreting the clues requires careful work and often involves comparing evidence from many different places and disciplines. Despite these challenges, a broad narrative emerges. There have been periods in Earth's history when the climate system behaved in a way that was strongly global. Snowball Earth episodes, greenhouse phases, widespread ocean anoxic events, and major shifts in atmospheric composition all appear in the geological record as planet-wide phenomena. There is a certain quiet drama in this. The planet does not shout its history, it whispers it, in ratios of atoms, in layers of sediment, in the shape of a scratched stone. Listening to those whispers requires patience and a willingness to think on timescales that stretch far beyond a human life. It's also worth reflecting on the idea that this record is incomplete. Many of the oldest rocks have been recycled back into the mantle through tectonic processes. Whole chapters of the planet's story have been erased or overwritten. What we have is a partial archive, one that still manages to convey a sense of the whole. In that sense, the memory of a global world is not just about what we can read in the rocks. It's also about what we infer, what we reconstruct, and what we imagine based on the patterns that remain. Science in this context becomes a kind of careful storytelling, grounded in evidence but open to revision as new clues come to light. The act of drilling into ice or rock to retrieve a core is, in a way, an act of reaching across time. A sample pulled from deep below the surface may contain material that last saw the light of day hundreds of millions of years ago. Holding it in your hand is like holding a fragment of a world that no longer exists, a world that moved to a different rhythm and followed a different set of rules. There is something quietly moving about that. The present moment, with all its complexity and immediacy, is layered on top of countless past moments, each one preserved in some form beneath our feet or locked in ice at the poles. The ground you walk on and the air you breathe are part of a continuum that stretches back to the earliest days of the planet. This perspective can change how you think about climate itself. It becomes not just a set of conditions you experience day to day, but a long unfolding process shaped by interactions between sunlight, atmosphere, ocean, rock, and life. The memory stored in the Earth reminds us that the system has moved through states far different from the one we know now. At the same time, those memories show patterns of connection and feedback that are still at work. The carbon cycle still links volcanoes, weathering oceans and atmosphere. The ocean still circulates heat and nutrients around the globe. The sky still forms clouds that reflect and trap sunlight. The planet is still, in its own way, a unified system, even if its regional expressions are more pronounced. The records in ice and rock also highlight how sensitive that system can be. Small changes in one part can, over time, lead to large changes in the whole. A shift in atmospheric composition, a rearrangement of continents, an increase in volcanic activity, or a change in the amount of sunlight reaching the surface can all set off chains of events that reshape the climate on a global scale. This doesn't mean the system is fragile in a simple sense. It has persisted through extremes that are hard to imagine, but it does mean that it is dynamic, responsive, and capable of moving into very different states. The patterns we see in those ancient records suggest that the Earth's climate system has a range of modes, some more unified, some more fragmented. The world we know now is one expression of that system, shaped by the particular arrangement of continents, the composition of the atmosphere, and the level of energy coming from the sun. Even now, in a world mapped by satellites and measured by sensors that circle the planet every day, there are moments when the deep past seems to brush lightly against the present. The patterns that once shaped a more unified Earth have not vanished. They have been folded into a more complex system, layered beneath regional climates, seasonal cycles, and human experience. When scientists look at the way air and water move today, or at how the atmosphere responds to changes in its composition, they often recognize familiar shapes in the data, echoes of processes that once operated on a far more global stage. Modern climate can feel like a patchwork. One place experiences drought while another floods. Heat waves strike one continent as cold snaps grip another. Yet, beneath this surface complexity, the planet still behaves as a single system. The atmosphere remains a continuous shell of gas that wraps around the globe. The oceans are still connected by deep currents that move water from one hemisphere to the other. Energy from the sun still enters at the top of the system and flows through every layer before some of it escapes back into space. One of the clearest ways to see this connection is through the movement of heat. The equator receives more sunlight than the poles, and that difference drives the circulation of both air and water. Warm air rises in tropical regions and moves toward higher latitudes. Cold air sinks near the poles and flows back toward the equator. The oceans perform a similar task, carrying warm water poleward near the surface and returning colder, denser water toward the equator in the deep sea. This large-scale circulation is the modern descendant of the broad, planetary patterns we've been tracing through the ancient world. The details have changed. The presence of continents, mountain ranges and ice caps adds layers of complexity. But the basic idea that the planet is constantly trying to redistribute energy remains the same. A good example of this is a phenomenon known as El Niño. It begins with a shift in ocean temperatures in the tropical Pacific. Warm water that is usually piled up in the western part of the ocean spreads eastward. This change alters the pattern of rising and sinking air in the atmosphere above. That, in turn, affects weather patterns across much of the globe. Rainfall increases in some regions, decreases in others. Temperatures shift. Storm tracks move. What starts as a regional change in ocean conditions becomes a global signal in the atmosphere. This kind of chain reaction is a modern illustration of how tightly linked the Earth system still is. It shows how a disturbance in one part of the planet can propagate through the air and water to influence conditions far away. Looking deeper, there are also echoes of the long-term carbon cycle that shaped ancient climates. Volcanoes continue to release carbon dioxide into the atmosphere, though at a much slower rate than human activities now do. Rain and rivers still weather rocks, drawing carbon out of the air and carrying it to the ocean. Marine organisms still build shells that eventually become part of seafloor sediments. This cycle is still operating in the background, even if its pace is often overshadowed by faster human-driven changes. The presence of this slow, geological process reminds us that the atmosphere and the solid Earth are still in conversation, still exchanging materials over timescales that stretch far beyond a human lifetime. The memory of Snowball Earth also lingers in the way scientists think about ice and reflection. Today's polar ice caps and glaciers are far smaller than the global ice cover of the deep past, but they still play a significant role in the climate system. Ice reflects sunlight. When ice expands, the planet reflects more energy and cools. When ice retreats, darker surfaces are exposed, more energy is absorbed and the planet warms. This feedback loop, which once may have driven the Earth into a near-total freeze, still operates in a more limited form. The difference is scale, not principle. The same basic physics applies whether the ice covers a continent or the entire globe. There are also traces of the ancient unified ocean in the way the modern seas respond to change. The deep ocean is slow to warm or cool. It acts as a reservoir of heat and carbon, absorbing large amounts of both from the atmosphere. This gives the climate system a kind of inertia. Changes at the surface can take decades, centuries, or longer to fully penetrate the depths. This slow response can make the climate feel stable on short timescales, even as long-term trends are building. It also means that what happens now can have effects that persist far into the future, carried forward by the movement of deep water masses that take centuries to complete their global circuits. Another echo of the past appears in the way clouds influence the planet's energy balance. As in the ancient world, clouds today both reflect sunlight and trap heat. Their overall effect depends on their type, altitude, and distribution. This makes them one of the most complex and uncertain elements in climate science. In a more unified climate system, broad changes in temperature and moisture would have influenced cloud cover over large areas. Today, regional variations play a bigger role, but the global patterns are still there. Shifts in sea surface temperatures can alter cloud formation across entire ocean basins. Changes in atmospheric circulation can move belts of cloud and rain north or south. These patterns connect distant regions through shared processes, much as they did in the deep past. A change in cloud cover over the tropics can influence how much energy reaches the planet as a whole, affecting temperatures far from where the clouds themselves are located. The The biological dimension of the climate system also carries forward ancient themes. Photosynthesis still shapes the composition of the atmosphere. Plants and algae absorb carbon dioxide and release oxygen, just as their microscopic ancestors did billions of years ago. The difference is scale and diversity. The living world now includes forests, grasslands, plankton blooms, and countless other forms of life that interact with the climate in complex ways. Forests, for example, influence local and regional climates by releasing moisture into the air through a process called transpiration. This moisture can contribute to cloud formation and rainfall. In large forested regions, this effect can help sustain wet conditions over wide areas. This creates a feedback loop between vegetation and climate, one that echoes the ancient relationship between early photosynthetic organisms and the atmosphere. At the same time, life continues to be shaped by climate. Species distributions, migration patterns, and ecosystems respond to changes in temperature and precipitation. In this way, the coevolution of life and climate that began in a more unified world continues in a more differentiated one. The geological record also offers perspective on the pace of change. Past climate shifts, even dramatic ones like snowball Earth or major greenhouse periods, unfolded over thousands to millions of years. The feedback loops that drove those changes operated slowly, allowing the system to adjust and in many cases stabilize in a new state. This doesn't mean the past was always gentle. There were periods of rapid change by geological standards, often associated with massive volcanic eruptions or asteroid impacts. These events could alter the climate and the biosphere in relatively short periods of time. Even then, however, the changes played out over spans that are long compared to a human lifetime. This perspective highlights something distinctive about the present. The rate at which the composition of the atmosphere is changing now is much faster than most natural processes that have shaped the climate in the past. From the standpoint of the long-term carbon cycle, it is a sudden pulse rather than a slow drift. Thinking about this in the context of Earth's deep history can be both grounding and unsettling. On the one hand, it reminds us that the planet has experienced a wide range of climate states and has, in some sense, endured through all of them. On the other hand, it shows that the system is capable of shifting into very different modes when certain thresholds are crossed. There are also modern parallels to the ancient idea of a unified climate in the way global monitoring works. Satellites observe the entire planet, tracking temperatures, cloud cover, ice extent, and ocean conditions. These observations reveal patterns that span continents and oceans, reinforcing the idea that local events are often part of larger connected processes. A heat wave in one region can be linked to a shift in atmospheric circulation that affects multiple parts of the globe. A change in ocean temperature in one basin can influence storm patterns in another. These connections, visible through modern data, mirror the global links that ancient records hint at. Even the way scientists build climate models reflects this perspective. These models treat the atmosphere, oceans, land, and ice as parts of a single system. They simulate how energy and matter move between these components, producing patterns that can be compared with observations. In doing so, they echo the ancient reality of a planet that has always been more than the sum of its parts. There is also a quieter, more personal way to notice these echoes. The air you breathe today contains molecules that have been cycling through the atmosphere and the oceans for centuries. Some of the carbon in those molecules may have been part of a forest, a plankton bloom, or a volcanic plume long ago. The water vapour in a cloud overhead may have evaporated from a distant sea and will eventually fall as rain somewhere else, continuing a journey that connects far-flung places. This sense of connection can make the present feel less isolated from the past. The climate you experience now is one expression of a system that has been evolving for billions of years. The patterns you see in the sky, the seasons you feel, and the landscapes you move through are shaped by processes that began long before humans appeared. At the same time, the past offers a kind of quiet guidance. It shows that the climate system is sensitive to changes in energy and composition. It shows that feedback loops can amplify small shifts into larger ones. It shows that the planet can move between different states of balance. These are not predictions in themselves, but they provide a framework for thinking about what is possible. They remind us that the Earth's climate is not fixed, but dynamic, capable of change on many scales. There is also something deeply human in the way we try to read these echoes. We drill into ice, chip away at rock, analyse tiny shells from the ocean floor, and turn those fragments into stories about worlds that no longer exist. In doing so, we place ourselves within a much larger narrative, one that stretches far beyond our own experience. That act of looking back can influence how we look forward. The memory of a global world, preserved in ancient materials, becomes part of how we think about the future of the planet. It doesn't offer simple answers, but it provides context, showing us the range of conditions the Earth has known and the processes that have shaped them. Some questions about the planet don't really point backward or forward. They seem to hover in the space between what has been and what might be, inviting you to hold both in mind at the same time. The idea of Earth returning to a single, more unified climate is one of those questions. It isn't just about predicting a future state. It's about understanding how the balance between all the moving parts of the planet could, under certain conditions, lean again towards something more global, more coordinated and less fragmented than what we experience now. To explore this, it helps to think of the climate system as a set of scales, rather than a switch. On one side are forces that create difference, contrast and regional variety. On the other side are forces that smooth, connect and unify. The planet's history is, in many ways, a record of how those scales have tipped back and forth over time. Today, the scales are weighted toward complexity. Continents are spread across many latitudes. Tall mountain ranges carve the atmosphere into distinct wind patterns. Large ice sheets sit at the poles, reflecting sunlight and reinforcing temperature differences. Forests, deserts, oceans, and cities each interact with the air and sunlight in their own ways. The result is a world of strong regional identities, where climate can change dramatically over relatively short distances. But beneath that complexity, the unifying forces are still there. The sun still delivers energy to the entire planet. The atmosphere still mixes gases around the globe. The oceans still connect distant regions through deep and surface currents. The long-term carbon cycle still links volcanoes, weathering, sediments, and the sky. These are the same broad mechanisms that once supported more global climate states in the deep past. So, what would it take for those unifying forces to dominate again? One way to approach this is to think about the role of contrast. Much of today's regional climate structure comes from strong differences between places. The contrast between warm tropics and cold poles drives powerful atmospheric circulation. The contrast between land and sea drives monsoons and seasonal wind patterns. The contrast between ice-covered surfaces and darker ice-free ones shapes how much sunlight is absorbed or reflected. If those contrasts were reduced, the climate system would begin to behave in a more unified way. That doesn't necessarily mean conditions would become identical everywhere, but the differences would be less sharp, and the dominant patterns would operate on a broader, more global scale. One factor that could reduce contrast is the distribution of ice. Large ice sheets at the poles create strong temperature gradients. They also act as bright mirrors, reflecting sunlight back into space. If, over a long period, those ice sheets were to shrink significantly or disappear, the poles would absorb more energy. This would narrow the temperature gap between equator and pole. With a smaller gap, the driving force behind some of the strongest wind systems would weaken. Atmospheric circulation might become broader and slower, with less sharply defined climate zones. Storm tracks could shift. The belts of rising and sinking air that define many of today's wet and dry regions might move or blur. This kind of change has happened before. During very warm periods in Earth's history, such as parts of the Cretaceous period, evidence suggests that the poles were much warmer than they are today. Fossils of plants and animals that prefer mild conditions have been found in what are now polar regions. The climate was not uniform, but it was more even than the one we know now. Another factor is the arrangement of continents. The current positions of land masses play a huge role in shaping ocean currents and atmospheric flow. If, over tens or hundreds of millions of years, continents were to move into a configuration that allowed more open, uninterrupted ocean circulation, the oceans could become more effective at spreading heat around the planet. Imagine a world where large land barriers no longer block the flow of warm water from the tropics toward the poles. In such a scenario, ocean currents could deliver more heat to high latitudes, reducing temperature differences and contributing to a more globally balanced climate. This is not purely hypothetical. The opening and closing of ocean gateways in the past have had major effects on climate. The formation of the Isthmus of Panama, for example, changed the circulation of the Atlantic and Pacific Oceans, and is thought to have influenced the development of ice sheets in the Northern Hemisphere. Over geological time, similar changes could push the system in the opposite direction. The composition of the atmosphere is another powerful lever. Greenhouse gases, especially carbon dioxide and methane, influence how much of the sun's energy is retained by the planet. Higher concentrations of these gases tend to warm the surface and reduce the likelihood of ice formation, particularly at high latitudes. In a warmer world, with less ice and snow, the surface would be darker on average. Darker surfaces absorb more sunlight, which leads to more warming. This creates a feedback loop that can reinforce a more even, global distribution of heat. At the same time, a warmer atmosphere can hold more water vapour, which is itself a greenhouse gas. More water vapour means a stronger overall greenhouse effect, further smoothing out temperature differences. The sky, in this sense, becomes a unifying layer, spreading warmth more evenly around the planet. Clouds complicate this picture, as they always do. Increased moisture can lead to more cloud cover, which might reflect more sunlight and counteract some of the warming. The balance between these effects is one of the most complex aspects of climate science. But on a broad scale, changes in atmospheric composition have the potential to shift the system toward either greater contrast or greater unity. It's also important to consider the role of the oceans as a kind of planetary buffer. The deep sea absorbs heat and carbon from the atmosphere and releases them slowly over time. This gives the climate system a long memory. Changes at the surface can take centuries or longer to fully penetrate the depths, and once they do, the effects can persist for a very long time. In a world moving toward a more unified climate, the oceans would likely play a central role in spreading that change. Warmer surface waters in one region would be carried to others by currents. Changes in salinity and density would alter the formation of deep water, influencing the global circulation that connects all the major basins. These processes operate on timescales that are far beyond any single human lifetime. They remind us that a shift toward a more globally coordinated climate would not be something that happens quickly. It would unfold over many generations, shaped by the slow movement of plates, the gradual adjustment of atmospheric chemistry, and the steady circulation of the oceans. Life itself would be part of this transition. The living world is not just a passive recipient of climate conditions, it actively modifies the atmosphere and the surface. Plants and algae remove carbon dioxide from the air and release oxygen. Forests influence rainfall patterns by returning moisture to the atmosphere. Microorganisms in the ocean play a role in the formation of clouds by producing compounds that affect aerosol formation. In a more unified climate, these biological processes would operate over larger, more connected regions. A change in vegetation in one part of the world could influence atmospheric composition and moisture patterns elsewhere. The feedbacks between life and climate would become more global in character. There is also the question of stability. The deep past shows us that more unified climate states can be both stable and extreme. Snowball Earth represents one kind of global state, where cold and ice dominated almost everywhere. Greenhouse worlds represent another, where warmth extended into high latitudes and ice was rare or absent. Neither of these states is necessarily balanced in a way that feels comfortable from a human perspective. They are balanced in the sense that the flows of energy and matter reach a temporary equilibrium, but that equilibrium can sit far from the conditions we're used to. This raises an interesting point. A move toward a more unified climate does not automatically mean a move toward a gentler or more moderate world. It could, under certain conditions, mean a world that is uniformly warm or uniformly cold, rather than one with a wide range of environments. The planet's history suggests that these global states often arise when feedback loops become strong and reinforce a particular trend. During Snowball Earth, the ice albedo feedback amplified cooling. During greenhouse periods, high levels of greenhouse gases and low reflectivity amplified warming. Once the system leaned far enough in one direction, it tended to stay there until another process pushed back. From this perspective, the idea of a fragile balance takes on a deeper meaning. The balance is not just between warm and cold or wet and dry. It is between the unifying and fragmenting tendencies of the Earth system. Small changes in one part of the system can, over time, shift that balance and lead to a very different global pattern. The present moment sits within this long context. The arrangement of continents, the presence of polar ice, the composition of the atmosphere, and the distribution of life all contribute to the current highly regionalized climate. At the same time, the unifying forces are still active, still shaping the system at a deeper level. When people talk about global climate change, they are in a sense acknowledging this underlying unity. Even though the effects are experienced locally, the drivers and feedbacks operate on a planetary scale. A change in atmospheric composition in one place affects temperatures everywhere. A shift in ocean circulation can influence weather patterns across multiple continents. This doesn't mean the world is on a simple path toward becoming a single, uniform climate again. The complexity of the modern system, with its many interacting parts, makes any such outcome uncertain and dependent on a wide range of factors. Over geological time, however, the possibility remains. Continents will continue to move, mountain ranges will erode and rise again, ice sheets will advance and retreat, the sun will slowly grow brighter. The long-term carbon cycle will keep exchanging material between the deep Earth and the atmosphere. Given enough time, these processes could align in a way that reduces regional contrasts and strengthens global connections. The planet could, in some future era, enter a state that feels, in broad terms, more unified than the one we know now. It's also worth considering that unified does not have to mean uniform. Even in ancient global climate states, there were still differences between places. The key distinction is one of scale. In a unified state, the dominant patterns operate at the planetary level, and local variations are shaped by those patterns rather than by highly localized features. In a fragmented state like the one we live in now, local features play a larger role. A mountain range can create a dramatic contrast between two regions that are geographically close, as coastline can separate a wet climate from a dry one. The global system still matters, but it is filtered through many layers of regional complexity. Thinking about this can bring a different perspective on the landscapes and weather patterns you experience every day. The rain that falls outside your window, the wind that moves the trees, the temperature of the air on your skin are all expressions of a system that spans the entire planet. They are local notes in a global composition. There is also a philosophical dimension to this question. Asking whether Earth could become one climate again is, in a way, asking about the nature of change itself. The planet is not static, it is a process. The states we observe are temporary arrangements within a much longer flow of energy and matter. From that point of view, the present, with all its complexity and variety, is just one moment in a long sequence. The unified worlds of the deep past were also just moments, even if they lasted millions of years. The idea of fragility comes from the fact that the balance between different forces can shift. The system can move toward more contrast or more unity, depending on how those forces interact. This doesn't happen at random. It follows the rules of physics, chemistry, and biology, but those rules can produce a wide range of outcomes. There is a certain quiet humility in recognizing this. The world we know is not the default or the final form of the planet. It is one expression of a much larger ongoing story. The deep past shows us that the Earth is capable of operating in very different modes. The present shows us a system that is both connected and complex, unified and regional at the same time. Holding those two views together can change the way the planet feels. It becomes not just a place of fixed environments and familiar patterns, but a dynamic, evolving whole, capable of reshaping itself in ways that stretch far beyond a single lifetime or even a single species. Long after the questions fade and the images of ice-covered oceans, shifting continents, and breathing stone begin to blur into a single slow-moving impression, what remains is the simple fact of where you are right now. You are resting on the surface of a planet that has been changing, adjusting, and remembering itself for billions of years. The ground beneath you is not just a place to stand or sit or lie down. It is a layer in a vast living archive, one page in a story that began long before there were eyes to see it or ears to hear it. If you let your attention drift outward for a moment, it can be almost surprising to realize how much of that story is still present, quietly, in the world around you. The air moving past your face is part of the same atmosphere that once held the gases released by ancient volcanoes and the oxygen produced by the first photosynthetic organisms. The water you drink or hear falling as rain has been circulating through oceans, clouds, rivers and ice for longer than any mountain range has stood. This sense of continuity can make the present feel both small and deeply connected at the same time. The climate you experience today, with its familiar seasons and regional patterns, is one expression of a system that has, at different times, behaved in ways that are almost unrecognizable by comparison. There were eras when ice reached into the tropics and the planet reflected much of the sun's energy back into space. There were others when warmth extended toward the poles, and forests grew in places that now see only snow and darkness for much of the year. Those ancient states are not gone in the sense of being erased. They are folded into the memory of the planet, preserved in rocks, in sediments, in the chemistry of the oceans, and in the slow movement of tectonic plates. They exist as patterns that scientists can uncover and as processes that continue to operate, even if their effects are expressed differently now. One of the quiet ideas running through this entire journey is that the Earth does not experience its climate as a series of disconnected events. It experiences it as a flow. Energy enters from the sun. Matter moves between rock, water, air, and life. Heat is absorbed, stored, and released. Over long spans of time, these flows create states that can feel stable, even though they are always at some level in motion. When you think about a planet remembering its oldest weather, it is not memory in the human sense. There is no awareness, no intention. Instead, there is structure. There are patterns that persist, mechanisms that continue to operate, and records that accumulate. The way carbon cycles between the atmosphere, the oceans, and the rocks today is shaped by the same basic chemistry that operated in the deep past. The way clouds form and influence temperature follows the same physical laws that govern the sky over a young world. Even the way continents drift, almost imperceptibly, is part of a rhythm that has been playing out for billions of years. Plates move, oceans open and close, mountains rise and erode. Each of these changes influences how air and water move across the surface, which in turn shapes the climate. The process is slow, but it is relentless, like a tide that never quite stops advancing and retreating. There is something quietly grounding about recognizing this. It can make the daily experience of weather feel like a small window into something much larger. A breeze on your skin is part of a circulation pattern that spans hemispheres. A cloud overhead is part of a cycle that links ocean, atmosphere, and land. A drop of rain is part of a journey that may have started thousands of kilometers away and will continue long after it touches the ground. The idea of a unified climate, which has guided this entire exploration, also leaves behind a certain perspective. It suggests that, beneath all the local differences and regional patterns, there is still a planetary system at work. The Earth is not just a collection of separate places, it is a connected whole, with each part influencing and being influenced by the others. That connection does not always feel obvious in everyday life. You might experience a sunny day or a cold night without thinking about distant oceans or faraway mountain ranges. But those distant features are, in subtle ways, part of what shapes the conditions you feel. The temperature of the air, the amount of moisture it holds, the direction of the wind, all of these are tied into a network of processes that span the globe. Looking back at the deep past can make this network feel even more tangible. When scientists find glacial deposits near the equator or tropical plant fossils near the poles, they are uncovering evidence of a planet that once organised itself very differently. Those discoveries don't just tell us about what the world used to be like. They also tell us something about what the world is capable of becoming. This is not about prediction in a narrow sense, it is about possibility. The range of climates Earth has experienced shows that the system has multiple ways of arranging itself. Some of those arrangements emphasize difference and regional variety. Others emphasize global coherence and planetary scale patterns. The present moment sits somewhere in between. The climate today is neither fully unified nor fully fragmented. It is a layered system where global connections operate through regional expressions. The atmosphere mixes gases around the world, but mountains and coastlines shape local weather. The oceans circulate heat across basins, but narrow passages and land barriers steer those flows into specific paths. In this layered world, it is possible to experience both connection and separation at the same time. A storm can be a local event, yet part of a larger pattern tied to ocean temperatures and atmospheric circulation on a global scale. A drought can affect a particular region, yet be influenced by shifts in wind patterns that span continents. There is a kind of quiet poetry in that, even without turning it into metaphor. The same physical laws apply everywhere. The same energy from the sun falls on every part of the planet. The same chemistry governs how gases and water interact. The differences we see arise from how those universal rules play out in different contexts. Resting with this idea can change how the planet feels. It becomes less like a backdrop and more like a participant, a system with its own rhythms and tendencies. The land, the sea, the sky, and the living world are all parts of a conversation that has been going on for a very long time. If you imagine stepping back far enough, the surface of the Earth becomes a moving pattern of light and dark, warmth and coolness, motion and stillness. Ice advances and retreats. Forests spread and contract. Deserts shift. Oceans rise and fall. Over millions of years, these changes leave traces that become part of the planet's memory. Those traces are not always easy to read, and they are never complete. Erosion, tectonic activity, and chemical alteration constantly rewrite the record. Whole chapters are lost. Others survive in fragments. The picture we build of the past is always partial, always open to revision, and yet, even with those limitations, the broad outlines are clear enough to tell a story of connection. A story where the atmosphere, the oceans, the rocks, and life itself are woven together in a system that operates across scales of time and space that are hard to fully grasp. There is also a human layer to this story, one that is easy to overlook when thinking in terms of deep time. The tools we use to uncover the planet's memory, drills that reach into ice, instruments that measure isotopes, satellites that scan the surface, are part of our own attempt to connect with something much larger than ourselves. They represent a desire to understand not just where we are, but how we came to be here. This desire does not change the planet. It changes us. It places our own experiences, our own concerns, within a much broader context. It reminds us that the conditions we take for granted are the result of a long chain of events, not a permanent feature of the world. At the same time, it can foster a certain sense of belonging. The carbon in your body was once part of the atmosphere or the ocean. The calcium in your bones may have been part of an ancient shell on the seafloor. The oxygen you breathe is the product of countless generations of photosynthetic life. In a very literal sense, you are made of the planet's history. This perspective does not require any particular conclusion or call to action. It simply invites attention. Attention to the way the world moves and changes, even when those changes are too slow to notice in a single lifetime. Attention to the connections between places that seem far apart. Attention to the layers of time that exist beneath the present moment. If you let that attention settle, the idea of a planet that remembers its oldest weather becomes less abstract. It becomes something you can feel in small ways, in the chill of a winter morning that echoes ancient glaciations, in the warmth of sunlight that has been driving the climate system since the planet formed, in the rhythm of rain that ties together sky, land, and sea. There is no need to rush toward an ending here. The story of Earth does not conclude. It continues, shaped by processes that are still unfolding. Continents are still moving, even if they shift by only a few centimeters a year. The atmosphere is still mixing and changing. The oceans are still circulating. Life is still evolving. In that sense, the planet is always in the middle of its own narrative. Every moment is both a result of what came before and a starting point for what comes next. From where you are now, you can think of yourself as resting on a thin, temporary surface between deep past and open future. Beneath you are layers of rock and sediment that hold the memory of ancient climates. Above you is a sky that will carry clouds, winds and light into moments that have not yet happened. The unified worlds of the deep past and the regional patterns of the present are not separate stories. They are different expressions of the same underlying system. The Earth shifts between them, guided by the flow of energy from the sun, the movement of material through rock and water and air, and the influence of life itself. If there is a quiet theme running through all of this, it is continuity. Change happens, sometimes slowly, sometimes in leaps, but the system itself persists. The planet does not forget in the way a person forgets. It carries its history forward in the structure of its processes, in the patterns that repeat and evolve over time. So, as this exploration comes to a gentle pause, there is no final statement to make, no conclusion to draw that would neatly wrap everything up. Instead, there is an open space, a moment to simply sit with the idea of a world that has been many things and will, in all likelihood, be many more. The air around you will keep moving. The ground beneath you will keep shifting even if you never feel it. The sky will keep forming clouds that drift and dissolve. The oceans will keep circulating water from one end of the planet to the other. And somewhere within all of that motion, the Earth will continue to carry the memory of its oldest weather, not as a story written in words, but as a living system that is always, quietly, writing its next line.